So our first speaker is Nick Swamy from Microsoft Research, and he's going to be talking about proof-oriented programming for cryptographic applications. So you want to try to share, Nick, and hopefully this will work.
Yeah, thanks, Andrew. Let me try. All right. Yeah, I'm sorry I'm not there in person. I was really looking forward to being there, but I've been nursing a kind of a sore throat for the last few days and figured it was better for me to not come there and give that, whatever it is, to you all. But I'm really happy to be here today. And I'm curious, how many people are in the room?
It's about 20 or 25.
All right, cool. Do interrupt with questions if as I speak, if something is not clear, and I hope we'll have some time at the end for questions as well. So I'm going to talk about proof-oriented programming for cryptographic applications, broadly in the context of this programming language and proof assistant called F-star that I've been working on for quite some time. This is joint work with really lots and lots of people. So I'm just summarizing and presenting the works of many others here. F-star, if you haven't heard of it before, F-star is a proof for, in the sense that it's a programming language that is integrated with a theorem prover, but with really a focus on programming, in the sense of including imperative features like state and exceptions and non-determinism and concurrency and so on. But F-star provides a logic that is expressive enough to state and attempt proofs of nearly any statement in mathematics, like other theorem provers like Coq and Lean and so on. But maybe what's distinctive about F-star is that it's integrated with the Z3 SMT solver, so that many proofs are automatic. And if you provide a few hints to the SMT solver, it can often find a proof for you. But the SMT solver is, especially when working in a logic as expressive as F-stars, is incomplete. And so when Z3 gives up, you can fall back on manual proofs by writing proofs by tactics or proofs explicitly writing proof terms. There's many options in F-star. I've been working on this for probably a dozen years or more, and while exploring the foundations of a programming language based on these ideas, we've also simultaneously been working on applications to evaluate these ideas. And especially in the last 5-6 years, a lot of these applications have come from cryptography. And I think it's been a really fertile intersection to design this programming language with these cryptographic applications in mind, and have really quick validation of new ideas in PL based on these examples from crypto. So I'll speak a bit about many of these applications. I'll touch on several of them in the course of this talk. So broadly, the way F-star works is that at the core, F-star is this programming language that's teams up with Z3 to try to prove things about your program. And once you've written your program and F-star agrees that it's correct, you can compile your program by default to OCaml or F# as two functional programming languages that F-star extracts to. But the one big idea in F-star is that it's a framework that's receptive to defining domain-specific languages for various programming tasks. So we have embedded in F-star a DSL that we call low star for low-level C programming, and you could write your program in low star, and by F-star can extract low star programs to C or to WebAssembly. But there are many DSLs in F-star, including one called Veil for writing verified assembly code, and it's actually the model of the assembly language that you work with in Veil is a parameter, so you can use it to target many different kinds of assembly languages. we've mostly been looking at generating x86 assembly, though there's been some work on producing ARM and things like that from Veil too. Recently, we've been working on a concurrent separation logic-based programming DSL called Steel. Steel can also extract to C, and we're recently looking at extracting Steel to Rust. This stack of DSLs continues. So we build verified parser generators on top of Lodestar and Steel, and these can be extracted to C as well. And on top of our parser generator, we have a new DSL for writing specifications in parsers and serializers for ASN.1, abstract syntax notation that's used in cryptographic certificates like X509. There's a paper coming up this week at Oakland about noise protocols. We've been looking at quantum programs in this DSL called QStar, and also been looking at doing proofs in our low-level languages of post-quantum crypto, implementations of post-quantum crypto primitives. And so it's quite a rich ecosystem of DSLs that feed into FStar and extract to these existing languages. To give you a flavor on just a simple example of how FStar works, so here's a kind of a sketch of how an implementation of Poly 1305, a specification of Poly 1305 and its extraction to C looks like in FStar. So I assume you can see my mouse too. So in FStar, you write a specification and an implementation of Poly 1305 in this model, in a monad, in an effect of FStar called ST that represents a stateful program operating over a C-like memory model. And in that specification language, you get to write a spec for Poly 1305 max that say that it transforms if you call it in a state where the initial heap contains both the message, the key, and the tag, then Poly 1305 terminates with in a final state H1 that only modifies the tag, and the content of the tag is equal to running this spec function on the content of the message and the key. And this spec function really is specifying a polynomial in GF 2 to the 130 minus 5. And so this is a precise functional spec of what Poly 1305 does. And you can implement this in FStar. And once FStar checks this, it can extract it to C. And what you get out is a C implementation that corresponds to the source FStar code. And all the checks are done statically at compile time. The theorem prover is proving that all these properties are true. So we're not inserting any runtime checks in the program to check various properties. So verification imposes no runtime performance overhead, and you get tight, high performance C code. So what do we prove? The things that we prove about our applications are, of course, it depends on what the application is. But as a general flavor of the categories of different kinds of properties we prove, I put them into sort of 4 buckets. As a baseline, we prove safety. So if we're producing C code, we always prove that the C code is memory and type safe, meaning that there are no abstraction violating pieces of code or undefined behaviors and so on. So no buffer overruns or dangling pointers or peeking beyond the abstractions that are enforced by the FStar abstraction mechanisms, the module system, and so on. We prove functional correctness, which is what I illustrated in the Poly 1305 example, that the imperative code matches some pure mathematical specification, and this prevents logic coding bugs. For where it's relevant, particularly in crypto implementations, we prove secrecy. So we prove, depending on the DSL, we have several models of side channel resistance. So for instance, in Veil, our assembly language, we have a certified analysis that proves that the Veil code is free from timing side channels in a model where the every Veil program produces an execution trace of program counters, and we prove that this trace is independent of the secret inputs to the Veil program. So yeah, secrecy where it's relevant, and also for things like cryptographic constructions or protocols, we prove cryptographic security. So where we kind of bound the probability that an adversary can break any secrecy or integrity properties of our code, and that's often done using a combination of meta theorems about the methodology that we're using to do these proofs, combined with machine checked proofs in F-star that automate the checking of a large chunk of the proof. But some of the proof is done on paper. So I thought I'd give a little taste of some notable F-star crypto developments. The first one that I wanted to point out is a library called PLCrypt. PLCrypt is a verified high-performance cryptographic provider. So what it does is we have many implementations of a wide variety of cryptographic algorithms and constructions. Many of them, well, a class of them that are written in portable C, and some of them that are written in platform-specific hand-optimized assembly. And what PLCrypt does is it packages all these implementations into a provider that does things like CPU auto detection to figure out, which particular implementation of I don't know, SHA-2 is the most appropriate for your platform. The APIs are grouped by family, so the way that their specs are written are to support cryptographic agility. So, for instance, all the hashes share specs that are instances of a generic framework for hashes. So this enables us to do proofs on top of these primitives in a very generic way. Overall, this library it produces about 80,000 lines of verified code, 65,000 lines of. This number is a little old, actually. The current numbers are a little bit more than this. So this is from 2020, about 2 years ago. We have about 65,000 lines of verified C code for the portable C implementations from Hacklestar, and about 15,000 lines of verified assembly that come from about twice as much code as that written in F-star. So across the entire library, the average sort of proof to code ratio is that we write around 2 lines of proof for every line of code that we ship in PLCrypt. And that's a very coarse measure. There are some parts of the library where the proof overhead is much greater, and there are some parts of the library where the proof overhead is maybe even inverted, where we get more lines of code out than lines of proof that we write by relying on techniques like metaprogramming and so on. But this at least gives you kind of a ballpark sense of the scale of the library, the scale of the effort that goes into the library. There's a paper from a couple of years ago at S&P describing PLCrypt. And since then, code from PLCrypt has been deployed in a number of places, including the Linux kernel, in Windows Azure, in Firefox, and so on. So that's been really great to see the adoption of this kind of high performance, high assurance crypto. I wanted to emphasize a little bit on the high performance part, and something that we're quite proud of is that we produce these high assurance implementations, but without compromising performance. So here's a little timeline of performance of various symmetric crypto and hash implementations, mostly the verified versions. But up here is at around 6.25 gigabytes per second of throughput is the fastest OpenSSL implementation of AES-GCM. We've been looking at verified crypto implementations for some time and making steady progress. But if you look at where we were, this is the Veil implementation of AES-CVC in 2017, which is quite a ways off. And then we had a POPL paper in 2019 where we had an implementation of AES-GCM in Veil, and it was the first verified one that we knew of that hit 1 gigabyte per second, but that was still a ways off of the fastest unverified implementation. And then with a lot of work and mainly from Chris Hoblitzel and Brian Parno and a few others, we managed to build a high performance implementation of Veil AES-GCM and whose performance exceeds that of OpenSSL by just a tiny bit. So I think our tools are reaching a point where it's possible to build these high performance implementations without compromising correctness and performance. So there's, I think, no reason to not use these kinds of verified implementations anymore. We've also been looking at protocol security. So at Oakland in 2017, we had a paper that was implementing and proving the TLS 1.3 record layer in FStar. And in the process of doing that, we found, and people from our team proposed fixes to the TLS 1.3 standard as it was emerging. And then last year, there was a paper by Antoine Delina, Lavo, and others also using FStar to build a security model and verified implementation of Quick. And that too has been a similar process, where the process of us investigating this protocol and the standard as it was emerging resulted in several improvements to the standard, which I think speaks to the ability and the interest of the community to use these kinds of tools in the process of designing these new protocols that are before they see really wide deployment, which I think is a really great trend. There's really a lot of stuff that of crypto in FStar, and I just wanted to highlight one of them, which if you're at Oakland this week, there's a paper by Sean Ho and others about Noise Star, where Noise is a small language in which you can write Diffie-Hellman style key exchange protocols, and they have a protocol compiler for Noise that proves the correctness and security of a whole class of these kinds of key exchanges. This is an instance where, by working at the right level of abstraction, Sean and his colleagues are able to sort of do 59 protocol proofs for the entire class of noise protocols for the kind of the cost of doing one generic proof. They get high performance C code for all noise protocols. So I kind of see it as sort of 59 protocol proofs for the cost of one. So that's a cool paper. You should check it out at Oakland if you're there. But for the rest of my time today, I was going to talk about something new, something called Zeta, which is a high assurance cryptographic safety monitor, safety property monitor that we've been working on recently. So the broad setting of Zeta is that it's kind of similar to the settings of some work in verifiable computation, where we have a client interacting with a stateful service, and the stateful service can be a database or a key value store or something. And the client is skeptical about whether or not the service is managing their data in a correct way, and correct in the sense of safety. So for instance, for a key value store, I think I'm back.
You are back.
That was an epic. epic fail. I think I'll just stop there, and we have 5 minutes left if there's any questions.
Okay, I mean, if you wanted to do some concluding slide or something just to set the stage for questions, that would be
Okay.
certainly fine.
Okay. I mean,
and by the way, if people have questions, well, I guess I'll try to relay them to the folks who are on Zoom because they probably won't be able to hear you.
okay. Well, let me just rather than putting slides up again, I'll just say a couple of words and to kind of I assume I got cut right at the time when I was talking about Zeta.
That's right.
Is that right?
Yes.
So I'll just say in a couple of sentences what Zeta is and what I was trying to work towards. So we've been working on this a way to add a cryptographic monitor to a stateful service in a style where if you have a service and you have a safety property that you're interested in enforcing on that service, what you can do is Zeta provides you with a set of building blocks that let you build an authenticated data structure that builds an abstraction of the memory of the entire service. And once you have that authenticated data structure that represents the entire memory, you can write policies, safety policies, or as abstract state machines that operate over this authenticated data structure. And what this lets you do is pair one of these runtime monitors along with your service so that when a client is interacting with the service and wants to know whether or not their state is being managed correctly, they can receive from this runtime monitor a certificate that attests to the fact that up to now, based on the trace of all the interactions that the client has had with the service, that trace adheres to whatever safety property that the client has chosen to instantiate the monitor with. So we've been using this to monitor key value stores at quite a high performance. So there's a key value store called Faster that provides around, by default, throughput of around 100 million operations per second. And by adding our this authenticated data structure-based monitor to Faster, we're able to provide safety property guarantees for Faster while incurring only about a 2x overhead. So we have around 50 million operations per second, but with the proof that every interaction with this key value service is correct in the sense of safety. So just to wrap up, what I was going to say was that I think PL plus crypto has been a really fruitful area for interactions. I really echo what Andrew was saying in his initial remarks. I think some of it has to do with crypto being, cryptographic implementations often having clear mathematical specifications of what the intended behavior is, which makes for a really good target for the proof-oriented programming. It's very clear exactly what theorem you're after. Even if you have a really large, complex, high-performance implementation, there's a really concise statement of correctness that you can exhibit as a spec. And I think it's also helped that there's broadly perceived wisdom in the software community to never roll your own crypto. So it's, people are willing to sort of leave their crypto implementations to experts. And that's allowed for people like teams of cryptographers and PL people to come in and do really high quality implementations and have them be deployed. So I'll stop there. Sorry for the tech snafu. And if there are any questions, I'll be happy to have them.
Great. I would a little applause for that. Okay, do we have time for a question or two? I know it's still early in the morning. So I actually have a couple of questions. So this data thing that you just told us about sounds pretty cool. So I guess as I'm understanding the way that you're using the authenticated data structures, it seems that you'd have to kind of build some kind of hash tree of the state of the application as it's being transformed.
That's right. Yeah.
And
Yeah.
I guess I'm impressed you can do things that quickly.
Yeah. So it's there's we use a combination of techniques. We use we have a new kind of a sparse Merkle tree construction that supports incremental updates, combined with a technique called deferred memory verification. It's Bloom set hashes, if that rings a bell to anyone. We use a combination of these two techniques of sparse Merkle trees and Bloom multi-set hashing, and this allows us to the sparseness and incrementality of the Merkle tree allows us to to not have to sort of every time you do an update, you can get by with doing just a constant number of operations to update the authenticated data structure. That's what makes it fast. We have a paper at SIGMOD in SIGMOD 2021. I can share my slides. There's a link on it that describes some of this work and an initial version of this work. And we're writing up a new version at the moment.
Great, thanks. Other questions? Andrew Miller has a question.
I really like this idea of like F-star and this approach being the end of don't roll your own crypto as like a necessary warning. Like it's safe to roll your own crypto as long as you meet the standard of satisfying the formal verification. I guess my questions are, is there something that would work for like symmetric key encryption, which tends not to have as clear like a proof structure, like it needs differential analysis to kind of justify that it's secure? Or, and I guess secondly, are there any examples of new cryptography that's only been created because of having the confidence of running it through something like F-star? You probably have to translate. I'm sorry.
Could you hear that okay?
Yeah, yeah, I could hear it. I could hear it fine. I think I'll take the second bit first. In terms of, so for instance, this proof of Zeta with this new Merkle tree construction and a hybrid thing that's combining Merkle trees with Bloom hashes and so on. It's super subtle, and there's in designing this thing, we're using F-star at every step of the way, and in the process of doing the proof, found and fixed many design bugs. It's not the kind of thing that I would expect. Like at least I don't think me and my colleagues would have been able to have much confidence in the correctness of that construction without tool assistance. So that's one instance of it. To your first question, I think there's degrees of correctness conditions that you can ask for. So at the very least, you can prove that the primitives that you're using to implement whatever symmetric key encryption construction that you're working with, like you can prove that the implementations are functionally correct, even if you don't prove cryptographic security mechanically.
Okay, great. Let's, I think, move. Oh, there's a great question on the chat. I wonder if there's any intention to verify differential privacy related implementation. There have been some papers on attacking improper DP implementations.
It's a great question.
I'm just going to start getting set up.
Nothing rings a bell at least nothing that I'm aware of at the moment, at least not in the F-star ecosystem. I might just be blanking on it right now, but it's a great direction to pursue.
So what you want to do is you need to join Zoom.
Okay, I'm sorry. Okay, that doesn't set you back. That's right.
Okay. And I think, can everybody on Zoom still see this? Yeah, okay.
All right.
Good.
Well, I want the camera. You know what? My laptop can go in.
There we go.
Yeah, this is perfect.
Okay, secondary coding.
Yeah, exactly. All right, perfect. Here, let me get this out of the way.
All right, I think close enough. All right, super. Thanks for having me here. I'm Andrew Miller from UIUC. I'm going to be talking about some joint work with my student, ongoing work actually with my student Surya Bakshi and our colleagues Ankush Das and Jan Hoffman at CMU, and Ankush is now at Amazon, and also some slightly earlier work I did with Kevin Lau, who's now at MIT, and Matt Hammer from Definity. This discussion has a position statement. I really want to try to convince you of something. So universal composability is an important framework in cryptography theory, but it's not really something that has any notion outside of cryptography theory. It's kind of deeply embedded within that field. And the viewpoint that I want to try to convey is that it's really time for PL people to lift this universal composability concept out of the depths of crypto papers and actually put it into the world of software development as well. I'm really interested in the smart contract and blockchain developer community. That's not essential to understand anything I'm going to talk about, but this is an especially ripe area. I'll give some of the reasons why I think this is like the destination or the subfield where this is really going to gain the most traction. So let me give you the very high level background of UC, and this is kind of the way that I try to explain it to protocol engineers. The whole point of this is to have a way of giving a security definition and an approach to proving security for your really complicated, messy, decentralized, distributed, fault-tolerant protocols. So UC concerns a real world and an ideal world. The real world is the world where you actually have your protocol, including all of its messy details involving communication between parties. We're usually interested in fault-tolerant protocols where someone's corrupted, you want security guarantees for everyone else. And your real world also includes any of the assumptions or primitives you make use of, like trusted setup for your cryptography or your peer-to-peer network you communicate over, or higher level primitives like a blockchain that's some shared resource that you would use. The ideal world is your pristine world that doesn't have any of those messy details. You just have a very simple communication pattern that makes use of this centralized trusted third party called the ideal functionality, which is just a hypothetical. It's for specification. We're not saying your protocols have to rely on a trusted third party, but just that this is a nice, clear, and simple way to approach saying what your protocol's behavior should be. And the whole point of the security definition of UC is to say that that real world with all of the messy protocol details is indistinguishable from this clean and simple specification world where you just have the ideal functionality. Now, the wisdom of UC is really about how to manage increasing complexity of complicated protocols that make use of things like this. So if you have multiple layers of increasingly complicated protocols, what you want to do is take this approach, which PL people will appreciate because it's the same kind of sentimentality of the value of compositionality. You don't want to analyze your whole protocol at once. You want to analyze a subportion of your protocol and as a component show that it realizes some ideal world specification. And then you can build a more complicated protocol by combining multiples of those, and then finally show that it realizes your overall specification goal. And this is kind of the wisdom that UC is centered around. So let me give just a little bit of details on why the blockchain research community is a good fit for this. The reason why is that the blockchain, there are a few reasons. So one is that this is already something that is adopted, and UC is adopted in cryptography theory. It's increasingly part of the computer security research world. Like a lot of computer security papers that aren't just cryptography actually have an appendix full of universal composability definitions as their main framework. So it's increasingly important. And in this subfield of off-chain and cross-blockchain protocols especially, all of the research uses this as their formal definition framework. The blockchain developer industry takes one of the most aggressive approaches to compositionality. They're structured as tons of independent developer teams that all build their own platform or layer that operate independently without coordination among these developer teams. And they all need to work together, so they value this kind of layered approach to abstraction in what they actually build. Another aspect is that the smart contract developers are already used to a rapidly shifting programming framework. There is almost like no baseline of what you have to expect that the software does. These are people that consume new research tools very rapidly and integrate it into their development practices. So this is one of the most kind of promising like venues to take your formal methods research and push it to an audience of developers who might use it. just to give a tiny like schematic structure of how to think about this aggressive approach to layers in a blockchain world. Blockchains are these nice synchronizing gadgets that mutually distrusting parties can use to work together productively, even though the parties don't trust each other. That's a layer that's actually built on top of a lower level peer-to-peer communication layer. And where the kind of research frontier of this is headed is more layers on top of this. So an important theme, a lot of research papers are on this, are about off-chain protocols where you don't always use the blockchain gadget, you do some peer-to-peer communication as well, but it's related to the on-chain actions. That's sometimes called layer 2 in the blockchain industry. And the kind of emerging topic now is about how to do protocols that actually span multiple different blockchains and their layers of off-chain or side-chain protocols. And altogether, you might call those layer 3. And each one of these really is like closely dependent on using the layer below it. And yeah, independent developer teams basically build their projects at each of these layers and have to work together. So away from blockchain, but just in terms of UC and formal verification, this isn't an entirely new topic. This is something that has been rapidly progressing recently. The 3 projects that I'm most interested in this line are EasyUC, which was built on top of EasyCrypt. Recently, EasyCrypt has internalized its own version of UC as well. So there's a whole UC branch of examples in the EasyCrypt formal verification system. And IPDL is another one along these lines, separate from the EasyCrypt stack with similar goals. To motivate the research that I'm going to talk about, the only comment that I would make about them is that these prioritize the successful end-to-end verification of their UC proofs. That's for sure the best goal to obtain. But the approach that they take towards modeling all of UC this way is to guarantee you get end-to-end verification, but target some restricted subset of UC. And what I will talk about is kind of switching the other way. Yeah, go ahead.
What exactly do they throw away from UC?
Mostly what they throw away is the open-ended flexibility of communication patterns. I'll give a couple of kind of examples for this, but in a nutshell, that's the thing that's most restricted. UC is extremely open and allows kind of complete flexibility to choose which of your possible outputs you will activate next. You can have communication that goes in a cycle, ping pong, or just like dumps all control to the adversary. And then the UC model is very open. If there's a composition theorem, it applies to all such adversaries that do that. And so generally to get a handle on it, you'll cover a restricted set that like subprotocols only follow a tree pattern or something hierarchical like that. And so one of my goals is to basically capture as much of the expressiveness of UC at our low level and push kind of those restrictions, as further down as possible.
But there are simpler forms of UC already in the literature.
Absolutely.
Are they adapting one of those or
they're making similar kinds of, I think, restrictions as those simplified versions of UC do.
Or model that you can point and say that's what they implemented.
No, I don't think that there's a single one to point to that subsumes specifically the restrictions that those all do. So what I'm going to talk about and I guess advocate for, and I'm saying it's complementary to this. So the end goal I think is the same. We want fully formally verified programming language tools and even ideally like automated proof search or automated synthesis of protocols just given a spec. The 2 approaches that I will talk about, first of all, are about building core calculus kind of language foundations at the very low level that are as close a match to UC as possible. And in particular, don't impose any restrictions. That the goal is to be as faithful to the original description of UC as possible. And the other complementary side is about embedding UC as a library in more general purpose languages that developers might already use or get some kind of benefit of. And the priority here would be to get incremental benefits from incorporating UC into your development style, even if it's far short of full verification of your proofs. So I'll give just enough of a background of a little bit more detail about what UC is, not enough to fully understand it, but just enough to appreciate a couple of concepts that'll come out in the language things that I'll mention later. So introduce the real and ideal world. In the real world, you have ideal functionalities representing your starting point. So your network assumptions, trusted setup, anything like that is the ideal functionality in your real world. On the ideal world on the right-hand side, you have an ideal functionality representing your application goal, the spec that you want to achieve. Naturally, in the real world, you have your protocol that is meant to implement the specification, and then you just have like pass through. There's no protocol where a protocol might be in that little corner on the right-hand side in the ideal world. What you do for constructing a proof is you say that the intuition is to say that any attack in the real world was also an attack that's possible in the ideal world. So, it's already kind of acknowledged by your specification, any attacker behavior. And the way this comes out in UC is you say for any adversary A in your real world, you have to show to complete your proof that you can construct a simulator S that plays the role of the adversary in the ideal world. And the idea is that these should be indistinguishable to an environment Z, which can be arbitrary, computational process, and it communicates with the adversary, and it also chooses the inputs to the protocol. So that's kind of the structure of it, and then the real and ideal should be indistinguishable for any such environment. One simplification I'll just show here because it's easier just to get it out of the way is called the dummy lemma. There's a strongest adversary, which is also the easiest adversary because it's just a pass through. And so really you just show that you can construct a simulator for the empty adversary case, and that's without loss of generality. That's enough for your proof. The first step, and this will come up a little bit later, is that because you have this environment that's the same in both worlds, the beginning point to derive your simulator is to say, well, the kinds of messages that the environment sends to the protocol as input in the real world, those are the exact same kinds of messages that the environment sends directly through honest parties to the ideal functionality in the ideal world. Similar for the environment communicating with corrupted parties in the real world, those are the kinds of messages going to the simulator. So the first step of UC analysis is basically doing essentially type unification, saying these kinds of messages in this context are the same types of messages in this other context, and that's how you organize your proof. I've tried to be like, and one of the things I'll try to do, I have like a backup slide made later, so I might not get to it, but have an experimental grad class where we cover UC proofs as the whole scope of it. So I've tried to do aggressive compression of the concepts into like meme format to help remember them. So I try to stick to a color code format for all of your UC development. Involves writing code for protocols, writing code for functionalities, writing code for simulators. And so it's helpful to keep track of which pseudocode. So I'll try to stick to a color scheme and even like an orientation to help keep track of those. I'll go over just one example, not in full detail, but just enough to understand a couple language concepts that show up later. So the example that is the starting example, and it really just keeps on giving, it's like the great example to cover most of the concepts in UC is on the commitment. Commitment starts with the sender committing to a bit. The receiver learns that a commitment has occurred, but no information about that bit. If the sender chooses, they can choose to open the bit that was previously stored. And then the sender learns that that's the bit that was opened. So this is an ideal functionality. You think of it as something incorruptible, but if you had this would do everything you would want a commitment protocol to do. If you are already familiar with cryptography, you might say, but not UC, you might say, well, I think of commitments as having a binding and hiding property. Where are these? I've just given you some code for a trusted third party to run, not properties, but you'd expect a binding statement and a hiding statement. And the way that these relate is that you say these properties are exhibited by this ideal functionality. So if you prove that your protocol is indistinguishable from the ideal world with this functionality, that's proving that your protocol also satisfies these properties. And how do you check that these properties are satisfied? Well, it should be clear just from inspection here, there's only like one code path where you can choose that bit. There's no way to get a B prime different than B sent out. So, it's an alternative to stating these properties, but it's consistent with stating those properties as well. And the functionality also has stronger properties like knowledge, but I won't go into that, but it's just enough to say it does exhibit those properties. So they haven't disappeared, they're still present. The protocol, as you might expect, I'm showing there's lots of ways of instantiating a commitment in UC. The easiest one, which is a little bit cheating, is to use a random oracle hash function. So this is the kind of standard commitment where you pick some nonce, hash it next to your bit. Your commitment is that hash, and the receiver can check that that hash recomputes the way you would expect when it's time to open it. I'll just show you a super high level aspect of the proof. Again, just enough to appreciate one thing that'll come up later. But there's a process for deriving the simulator. And again, it starts from identifying the kinds of messages that the simulator would have to receive in order to present this indistinguishable view to the environment. So if the environment interacting with the ideal functionality takes the form of that commit message with the bit and open containing nothing, that's the same as what the environment would send to the protocol. Similarly, the real world protocol details blue, which include the actual hash, the actual nonce that's part of the protocol. If that's what the environment would send through the pass-through adversary to the random oracle in the real world, those are also the same kinds of messages that the simulator receives from the environment. So you follow this kind of arrow tracing and you start to learn what are the inputs and outputs that the simulator you want to construct has to take and has to produce. And the last concept is that nearly every simulator, and I think it's true for absolutely all simulators, depending on how you zoom out, every simulator will contain within it a simulation of the entire execution experiment of the real world inside it. So the simulator lives in the ideal world, but it has like a thought bubble, a local simulation of a real world protocol running within it, with some caveats depending on like how you hook up the arrows and interpose them in some different ways. But this is kind of the high level view of what a simulator ends up looking like. So that's not enough details to understand the commitment proof, but just well, you'll see why a couple of things come back a little later. So I'm going to come back to this commitment example, and I mentioned that I'll follow these kind of two paths. One's about designing a core calculus that's a good match for UC, and the other is about embedding this in a general purpose language. This is what a pseudocode for this F commitment looks like that you would see in a paper. This is what our core calculus, interactive lambda calculus looks like. It has linear types and communication over channels. I'll say a bit more about that. And this is what the same commitment ideal functionality looks like in Haskell Saucy, which is our general purpose language we've made a UC library for. So I'll start by talking a little bit about the core calculus before talking about Haskell Saucy. And I'll just make a couple of points here. So the first one is, what's the essential challenge with trying to build a core calculus that's as flexible as UC, but not worse, or not too expressive compared to UC? Because this involves communicating over channels between different processes, I thought PyCalculus is the most natural starting point for a core calculus that's a good match for UC. One of the challenges with PyCalculus, though, is that it has non-determinism. There are potentially many different ways of starting from the same PyCalculus term, and you might arrive at many different results. The possible choices to make at each step are essentially resolving race conditions, scheduling which message gets sent to which process first. And that's not something that appears in UC at all. In UC, there's no unbounded non-determinism like you find in PyCalculus. The rationale for this is that in UC, it's very important that the entire execution of this experiment can be carried out by a probabilistic polynomial time Turing machine, which has like probabilistic interpretation, not like an unbounded set of possible choices. So that's this kind of first mismatch. A schematic of what it looks like to watch processes in UC run is that there's always exactly one running at any given time. Processes have some number of outgoing tapes, some number of incoming tapes. If a process writes on one of its write tapes, the process on the other end of that tape is immediately activated and starts running. There's only ever one process running at a time. Control passes from one to another, but it's actually an entirely deterministic execution pattern. There is randomization, these are probabilistic, but you can determinize that by just treating all the random choices as coming on a coin input tape. And so if you consider the coin flips as part of the input, then everything else altogether is entirely deterministic. So the core of our challenge is to try to design a type discipline for the PyCalculus that coincides with the way that interactive Turing machines that UC is built on run. I'll give just a couple of kind of, hopefully it's enough to just kind of understand the main idea of how this is implemented. The way that we do this through ILC is by using a linear, or more specifically an affine type system. And the idea is that the read ends of channels are a linear resource. You can't make two copies of them. That wouldn't make sense in ITM. So we make a type rule that says that it doesn't occur in our ILC either. Our type judgments have kind of this form. You're evaluating a process expression E. You have some context of linear variables that's in, also some context of variables out. You have lots of data that aren't the linear contexts here are just for the channels and for a write token that'll come up later. And so let me skip to the main. So this is the main idea. These are the type rules for writing and for reading on a channel. And the main idea is that we keep track of a linear entity called the write token, which in order to write to a channel, you have to be holding the write token. And by writing to this channel, you're giving up that write token. And that's what this rule says. A write expression starts by having the write token, but then it's consumed by the time you're done writing. And kind of dually for reading, if you start out by reading, you don't have the write token, but as a consequence of reading, you get activated and now you have it. So basically these linear typing rules force that property of determinism is exactly present in any well-typed pi calculus term that satisfies this. So it's like a subset of pi calculus induced by adding these linear terms that causes it to coincide with what you can do in interactive Turing machines. There are a couple more aspects to this, but that's kind of the key one. And it gives the flavor of kind of using this to kind of squish everything down so that it's consistent with ITMs. There's a lot more detail in the PLDI paper where we did this. I want to mention kind of what's the next step and what's our ongoing work with this aspect of the research. One of the things that's missing from ILC, and one of the most challenging things I think in UC is keeping track of polynomial runtime. We need polynomially bounded computations for the cryptography interpretation to make sense. The way that this is done in UC is actually extremely interesting and subtle, and it's called import tokens. And the motivation here is you don't want to rule out simple servers like ping, like a echo server that just receives a message and responds to it. But you also can't like hook up two of those together because they would ping pong back and forth forever without end. But you don't want to introduce artificial limitations, like every process has to have some fixed budget, regardless of what happens outside. Those end up being too restrictive. So the import tokens in UC says that you have these notions of import tokens, you can send and receive them on channels, but there's a rule you have to respect, which is that the total amount of steps that your process has taken has to be some polynomially bounded function of the net amount of import tokens you're holding on to. So it's kind of thematically a little bit like gas, if you're used to smart contracts at all, but it's a bit different as well because it includes this polynomial slack. And so I guess I won't try to go into clear enough detail of this, but all I will try to say is that it's possible to take this notion of import tokens from UC and also build it into the same kind of approach of using linear type system in order to basically ensure that you have the way that we do it is by starting from a language called Nomos, which is a resource-aware language. It uses a notion of potential. That's like one-to-one with computation steps. 1 unit of potential means 1 computation step. But to manage the UC notion of import, you have to have this polynomial slack. So the difference between import and potential is 1 unit of potential is 1 unit of computation, but 1 token of import could possibly be a much larger amount of computation up to an arbitrary polynomial function. And so, we basically design a typing rule where you can convert your import tokens into potential in order to take execution steps, but you have to ensure that you have some polynomial budget and you never bust that budget throughout the execution of your process. And in a nutshell, this is kind of, again, adding to our type system in order to reconcile a difference between how UC works and what a traditional core communicating calculus does. So let me switch to just talking about a couple of highlights from our Haskell saucy direction. So first of all, these will just be a couple of high-level bullet points, but this is maybe an open-ended question. I'm curious if you all have ideas. Is that someone a question on Zoom? Might have been background noise. All right. So what would it mean for developers, not just security analysts, to incorporate UC in some way into their development? So the first thing is I think of ideal functionalities as a kind of executable API documentation. It's like an upgraded form of API documentation. It's API documentation you could actually run. An analogy that I make is that you can think of ideal functionalities are for fault-tolerant protocols what mock objects would be for an object-oriented programming. It's like an idealized version of a subcomponent of your overall development that's useful in testing. You can think of ideal functionalities as the same thing, but for these fault-tolerant protocols, not just object-oriented programs. Environments are these test cases. Like a protocol will be indistinguishable for any environment you can throw at it. That suggests that you could use fuzz testing to find environments that demonstrate that you failed to make your protocol secure. And even if we take this approach of not aiming for full formal verification, you can still get a lot of benefits by running it through just a type checker and just having something you can run. It helps catch a lot of kind of simple mistakes in edge cases. So I'll just show, I'll say a couple of high-level things and then just show a couple of highlights. So Haskell Saucy is our attempt to build a universal composability library on top of Haskell. We can build it on top of the existing channels abstractions that Haskell has. What we're missing out though is that it's not a sound type system. Like you can write things in this library that are not actually meaningful in the world of ITM. So you kind of have to have the typing rules from ILC in mind and just check by your own inspection that you aren't violating one of those rules. To fully integrate that would be a nice future work. What we provide then are a bunch of type class layers for each of the different components that you would have to define, the functionalities, protocols, simulators, and these provide the environment keywords that you would need to be able to define all of these. So I'll just show a couple of highlights. So the first thing is that the UC execution experiment is something that we implement in our language on top of this underlying ITM abstraction. The main work that this execution experiment does is just running each of these components of the experiment and simply hooking up the channels together according to that quad chart so that they all match. What you get by doing this is that type unification of chasing the arrow colors around to figure out what your simulator can do. That's actually now something that the type checker output will give you. If you use something like wildcards, it'll actually start telling you what kinds of messages you should be putting there. So this is a good way to help you figure out what your simulator, if one exists, needs to be able to do. Every simulator that we write ends up having in some form an internal simulation of the exec-UC experiment within it. And we can actually literally get that. We get this because our implementation of exec-UC is just on top of our ITMs layer. And so you can write ITM code that includes running exec-UC. So it gives you a principled approach to building these kinds of simulators. You can write test cases. Test cases are the form of an environment. The environment chooses inputs for the honest parties and tells the corrupt parties what to do. And because if your protocol is UC secure, this works for any environment. This is how you make test cases. Any test case you can write, if your protocol is secure, it will fail to distinguish the two worlds. So it gives you an approach to gradually making more test cases that cover your protocol. UC is based on adding like layers of abstraction. Most UC projects don't just write something in UC, but they define a new UC wrapper that gives like a new class of functionalities extended with some extra ability. And so this is something that we do. So this is one of the most important ones. It's modeling an asynchronous eventual delivery communication network. So we extend our functionality type class with a new keyword eventually. And this is all just implemented, within this library. And what this allows you to do is say, here's an ideal functionality for reliable broadcast is this example. Well, when it gets a message to deliver, it goes through all of the possible receivers. And for each one of them, it schedules for eventual delivery a task that delivers them the message. And that's what the intent of reliable broadcast primitive is. And then under the hood, this is implemented just using the same channels. It builds like a run queue and allows the adversary to determine the order that these are delivered. So this is a work in progress. We're doing this in the open, so there's no, you could go look at the code that we have so far. Roughly where we are is that we've implemented a good portion of the very basics of UC in several examples. We're really interested in working on broadcast protocols where we can especially focus on a liveness guarantee. This is usually not the one that formal verification will check. You check your safety properties, but liveness is trickier. We're not formally verifying any of this, but we're expressing the liveness properties, and the simulator has to simulate liveness properties. And our upcoming work that we're striving towards is including layers of a model of blockchains and smart contracts and these off-chain protocols. So I will wrap up. These are kind of my guess, repeated concluding, remarks. So this is a standard framework in cryptography, but it has yet to catch on in software, but I think that's where it has a lot of potential. Maybe I'll just say this because I haven't said it yet. A lot of the things that I find interesting in UC, especially the edge cases or the things where maybe it's ambiguous when you find a UC pseudocode in a paper, these are not interesting from a cryptographer's perspective. They're not really about new hardness assumptions or about real errors. They're really just kind of bookkeeping details. But I find them fascinating, and I think that's really what a programming languages person would find as well. So my claim is that basically the edge cases and things that make UC somewhat cumbersome in cryptography theory, well, the right approach to take from them is a PL person's approach. So that's why I think this is a really important area for the PL plus crypto zone to focus on. So I have some links. I expect we'll have our Nomos UC preprint, which covers that potential typing rules. Unfortunately, that's not online for now, but this is something that will be up soon. And some of these other links are available there. All right, I'll stop there and see if there's any time for questions. Thanks.
Okay, thank you. Maybe just one question? Yeah.
Yep.
Introduce yourself. Oh, I'm Stefan Dragonas. I work at SRI.
Awesome.
I have a question. So the question of indistinguishability between the idea of functionality and the real world functionality, where does that come into play in this ecosystem? Social typing system?
Yeah. So
restate the question.
Okay, so to restate the question, you say, where does this notion of indistinguishability come in this ecosystem of software tools? So, I mean, this is the way to view it. The real indistinguishability says, universally quantified over all possible environments, it's indistinguishable for any environment. And if you had a logic system and the other formal verification related work I mentioned are able to make such universally quantified statements, since we don't have that, the best we can do is offer a framework you can write such test cases. And the rule is that if you can find, if it is secure, then you will not be able to find a test case that works. So you can try to enumerate or fuzz test or just come up with the most interesting test cases. If your protocol is secure, those will all fail to distinguish. And if you can show one that does distinguish, then that gives you a way to show that it didn't work. Right now, most software doesn't come with any specification at all. So it would be a huge paradigm advance to merely make the software projects falsifiable by including a specification. And then if they're wrong, and someone could come up with an environment that demonstrates that they're wrong. Sure.
Okay, great. Let's take further questions.
All right. Thank you all very much.
We'll 10-minute break and then we'll get started with the next section. Okay, so we'll start the second session. The first speaker is George Ajay from Brunel.
Right. Hi, Josh Ajay. I'll be talking about Viaduct, which is a compiler we built for security distributed programs that compile down to cryptography. So this is joint. This is joint work with Rolf Recto. Josh Gancher will be giving a talk later today. Andrew Myers and Elaine Shi. So the general premise is secure distributed applications need cryptography. That's just the fact. So anytime you're doing, secure cloud storage, privacy preserving blockchains or machine learning, you need to use crypto. But cryptography is notoriously difficult to get right. So I don't know. Is this working? Hello. I think it's turned off. Okay, there. All right. Better?
Yeah.
So cryptography is notoriously difficult to get right. Prior research has shown time and again that developers misuse and misunderstand cryptographic APIs. And this isn't just a matter of rolling your own cryptography. This is just people using existing libraries incorrectly. Our solution to this problem is to abstract cryptography completely away from the programmers. So programmers write their programs or write their applications in a high-level language and specify the security policies of their applications declaratively. And then the Viaduct compiler will essentially figure out what cryptographic protocols are secure or safe to use, and it will compose them correctly also. There is, of course, prior work that has similar goals, but most existing compilers are limited to a fixed set of protocols, which is usually just one protocol. So, Fair Play and Oblivion generally, just compile down to MPC, secure multi-party computation. They're compilers for homomorphic encryption and zero knowledge proofs. And then the problem with this is, of course, real applications need to mix mechanisms. You can't take your entire application, turn it into one circuit, and run it efficiently. And if you need to mix protocols, if developers need to mix protocols, well, vulnerabilities creep in at the seams. So when you're composing protocols, you might make a mistake. The novelty with LIDAC is that it can target essentially an arbitrary set of protocols. It is an extensible compiler, and it a priori doesn't actually know anything about any of these protocols. You can actually teach the compiler about what MPC means or what replication means. And it can actually mix multiple protocols in a single program. So how do we decide which protocols to use? And the key insight that makes all of this possible is we use information flow labels to kind of mediate between cryptography, the security guarantees provided by cryptographic protocols, and the security requirements of programs. So I'll give a really quick primer on information flow labels. We are interested in confidentiality and integrity. So labels are just pairs. Each component of a pair is essentially a Boolean formula. So we have and or, and we have a bunch of base principles like ABC, probably standing for Alice, Bob, and Chuck, whatever. And implication really means acts for or has more authority than. So, Alice and Bob implies Alice, which means Alice and Bob has more authority than just Alice. Using labels, we can describe the security properties of protocols. So the simplest protocol is local computation. If you just you use plain text to run computation on Alice's machine, that has the same label as Alice, or the host H. A more interesting protocol is clear text replication. You replicate the same data on computation on two hosts and check the hosts against each other. This gives you higher integrity. So the integrity label goes up to the end of the hosts that are involved in replication, but any host can see the public data. So confidentiality is lower. So it's the order of the confidentiality. MPC, or maliciously secure MPC, gives you both high secrecy and high integrity. We have other protocols like commitments are like replication. They give you high integrity, but you're only storing hashes on one machine. So confidentiality doesn't go down, or the confidentiality is whoever has the clear text value, and you get the integrity of both parties. We can also support semi-honest MPC, but that has a more complicated label. We can discuss it offline. And I'll give a little overview of the architecture of the compiler. So you start with a source program, and then there are two main phases. We do label inference, which puts a label on every single program component, and then we do protocol selection. Label inference computes the security requirements of the programs. That's the first half, and protocol selection essentially solves an optimization problem. So it's deciding what protocols are safe to use, and if there are multiple protocols, which one will give us the most efficient implementation. Finally, there's an extensible runtime system that executes the compiled programs. And there's a bunch of well-defined extension points. These are interfaces in Java or Kotlin. And this is how you teach the compiler about new protocols. Let's look at an example program. So this is the classic millionaire's problem with a twist. So instead of, so here we have Alice and Bob who want to figure out who was richer at their poorest. So the idea is Alice and Bob both input a series of values. It's 3 for this example. We compute the minimum of these values, and then we do a less than comparison, and then we output the result to both parties. The thing to note about this program is that there's no mention of cryptographic protocols. That's LIDAC's job to figure out. There are some conspicuously missing white space there, which I'm going to fill out right now. But so that's how we talk about the security policy of the program. So the first thing we need to do is we declare the hosts in the program, and we give them labels. In this case, Alice and Bob are mutually distrusting, so I'll give them two labels that are independent. So Alice has, Alice A confidentiality and integrity. Bob has B confidentiality and B integrity. Next, so the minima when you compute them, if I just use Alice's data to compute it, that is only trusted by Alice. But ultimately, I want the result of the comparison to be trusted by both parties. So I need to endorse the result of this computation and say, after the minimum is computed, I will just trust the value. And we do the same with Bob's inputs. This less than includes data that is secret to both Alice and Bob. So a priori, you cannot output this to just Alice because Alice is not allowed to read it. I can explicitly declare that it is okay for the result to be visible to both parties using a declassify expression. Next, this is an example program. There's actually a lot of labels that you have to specify, but in general, you don't have to specify that many labels for programs. All the missing labels need to be inferred by the compiler, and it does that by running a classic, information flow analysis to determine what labels are possible. But we actually have different requirements for Viaduct, which is we don't normally with a program language that has information flow labels, you're only interested in whether there is a solution or not to all the constraints in the program. For Viaduct, we actually want a specific solution, which is a minimum authority solution, because more authority means more trust, and more trust can only be achieved using more expensive cryptography. So Viaduct can look at this program and see that, okay, Alice's data is trusted by Alice. So, the A1 through A3, and also the minimum of those things has the label A comma A, which is the label of Alice. Same with Bob's data. Once you endorse it, you are increasing integrity, but you're not changing confidentiality. A less than B has a computed label, which is, it has the secrecy and the integrity of both of those, both Alice and Bob. And then once you declassify it, it is made visible to both parties. Then we do protocol selection, which essentially follows, is based on these labels and the table that I showed you. So protocol selection, as I said, is trying to figure out what protocols are safe. It's also trying to minimize execution costs and communication costs. So, prefer replication and commitments over MPC, and try to minimize data movement between hosts. So we can look at this program and say, well, minimum of A1 and A through A3, that only needs Alice's integrity and confidentiality. We can compute that locally on Alice. Same with Bob, but after endorsing it, the less than needs to be computed using MPC, because that we need high secrecy and high integrity for that. And MPC is the only protocol that can give us that. Once you declassify the data, now it has lower confidentiality, but still has high integrity. So we need to replicate it on Alice and Bob. And then we can output the value to both parties. I'm not going to go into the details of the runtime system too much, but I just want to show you this picture. So essentially, we start with a source program. Protocol selection really gives us a partitioning of the program. So you say, these chunks are running on local of Alice. These chunks are running on MPC between Alice and Bob. And we have like all these separate, essentially idealized protocols running some code, but that's not, you don't actually have an MPC host in the real world. So the runtime system needs to essentially implement MPC using, implement MPC on Alice's machine and on using threads running on Alice's machine and threads running on Bob's machine. So I only showed you one example, but we have implemented larger examples. There are a bunch of MPC protocols that also use, that use that mix MPC with local computation or replication. We have a Battleship example that uses zero knowledge proofs and replication. And of course, we don't tell Viaduct to use zero knowledge proofs. It figures out that it doesn't need to use MPC, so you can actually use only zero knowledge proofs, which are potentially slightly cheaper. We do have an example that uses both zero knowledge proofs and MPC at different parts of the program. And the idea is Viaduct can figure out what an efficient protocol is on its own. This is kind of showing the impact of you not just using MPC for your entire program. So local computation and using replication of cheaper protocols can actually save you significant amounts of overhead. So we can get speed ups like 2x or 4x speed ups depending on how much of the computation you're doing locally. I want to shift tracks here a little bit and talk about how we actually prove the correctness of the compiler. So at a high level, any compiler, and specifically Viaduct, is correct if the generated code maintains, specifically the security properties of the source programs. This means developers can reason at the source level, so you can just look at your source program and realize that these are all the properties that it has, and Viaduct will not violate anything that you expect of this program when it does the compilation. Because we are targeting cryptographic protocols, we actually want to use universal composability as opposed to something like full abstraction or some sort of hyperparameter preservation result. So thank you, Andrew Miller, for introducing UC, so I can fly through these slides slightly faster. But the idea, just as a refresher, is that we have a real world that we're comparing against an ideal world. The real world is this complicated thing where you're running, all of these hosts are communicating with each other. There's an adversary that can intercept all the messages in the middle and also gets the schedule of these protocols. Whereas the ideal world is essentially thinking to be obviously correct. It is a single-threaded program running on a single machine with a very well-defined interface. So it is easy to look at it and figure out what the security properties of that program is. And showing a UC simulation really comes down to showing that every attack that was possible on the real system, it can be translated to an attack on the ideal system. And because we are okay with all the attacks on the ideal system, by definition, the real world can be no less secure than the ideal system. For our purposes, we take the proof down to a hybrid level. So instead of saying, Alice and Bob are running a bunch of code, which includes, pieces of an MPC protocol, MPC is actually a separate idealized host or, a hybrid functionality in crypto parlance. So that we have, Alice, Bob communicating with all the protocols like MPC and zero knowledge proofs, and they're all treated as hosts. And we want to show that this thing simulates the original source program. And the idea is if we do all these words in UC, because UC is composable, if somebody else separately proves that, this MPC protocol actually satisfies this interface or this MPC box that you defined, then we can get an end-to-end proof. The main challenge with a UC proof is that the target adversary is seemingly more powerful than a source adversary. So the entire proof comes down to showing that this is not really the case. But for us, the target programs, the adversary has, can corrupt intermediate data, whereas in the source programs, it only interacts with the program through input and output. And it controls all scheduling in target programs, whereas in source programs, there's no scheduling decisions to be made. You just say, take a step and take another step. Because UC simulation is transitive, we can break up the proof into small steps that kind of individually address the problems that, or the challenges that I talked about. So the first step, we essentially, let me step back a little. So in this picture, compilation is going from right to left. So we start with a source program. We do protocol selection, which gives us a protocol annotation for every piece of code in the program. Then partitioning turns into the distributed hybrid model that I showed you. And then simulation goes the other way. Essentially, we're trying to go from the target distributed program back to the source program. And each step deals with the problems we talked about. So to show that corrupting intermediate values are not useful, we actually show that you can erase all data coming from the adversary or replace it with a zero, which kind of implies that whatever control the adversary had is actually not useful, because putting zero for all of those is as good as anything else. Then we do a sequentialization step, which is, in a distributed program, you can maybe reorder events, but we're showing that, whatever orderings that you have are equivalent to the orderings that were possible in the sequential source program. I will only talk about the first step of this through an example. So I said we're trying to erase all the data that is controlled by the adversary. So On the left, we have a program where, Alice has the label, the variable X, and she's sending it to Bob and Chuck. So Bob and Chuck receive X from Alice. Essentially, because Alice is corrupted in this case, we want to show that, instead of receiving a value from Alice, we could just put 0 there. The thing that makes this step tricky is the next thing this program does is send X plus 1 back to Alice. So in the program on the left, if Alice sends 5 to Bob, then Bob will send back 6. The program on the right, whatever, Alice is not sending anything to Bob. Bob will always respond with 1, which is different from 6. So simulation doesn't hold unless the simulator can fix the difference or cover up the difference. The main idea, as with most simulation proofs, is that the simulator maintains a public view of the entire execution. So this includes, all the hosts, all the honest hosts, the network and the adversary. And the proof really comes down to showing that, the target program, which had all the data, public, secret, trusted, and untrusted data, can actually be simulated by the trusted target program, which only has trusted data. So it has all the untrusted data has been erased. The simulator, which only has a public view of the program. And these things together can actually recover all of the data in the original program. And this is only possible due to information flow checking in target programs. So I said, normally for a compiler, you would prove something like, full abstraction or property preservation, but we did a UC proof. So a useful property to prove about compilers is robust hyperproperty preservation, which was, identified along with a bunch of other properties that you might care about in this paper called Journey Beyond Full Abstraction. At a very high level, this just says your compiler preserves all hyperproperties of source programs. And we actually prove that simulation, UC style simulation, implies robust hyperproperty preservation. So we do, the compiler actually does preserve, all security properties like non-interference of source programs and target programs. The main takeaways with Viaduct are that, information flow label, we use information flow labels to mediate the security of crypto protocols and programs. And Viaduct can mix multiple cryptographic protocols in the same program. And labels enable compositional reasoning about cryptographic protocols. Some ongoing work. Right now, we show that taking a source program down to the hybrid level is secure. We did that part of the proof, but we haven't currently instantiated these idealized boxes like MPC with real protocols. So we would like to get a full end-to-end UC proof, ideally verified in, EasyCrypt or one of those tools. We are working on an intermediate language for circuits. So one thing we realize is a lot of protocols like MPCs or not sure, some work in encryption, they compile down to circuits. And right now we have this ad hoc thing where, we're doing something to generate MPC circuits and something else for generating zero knowledge circuits. It would be nice to have a unified intermediate language where we can essentially do like generic optimizations over circuits. There have been some attempts at doing this, so we might try to compile down to one of those tools like circ-C is one. And the final thing another thing we want to add are availability policies. So if you are familiar with security, generally people talk about the CIA triad, so confidentiality, integrity, and availability. Adding availability to Viaduct allows us to differentiate between more protocols. So one thing we can't do right now is, differentiate why, say, MPC is different from something like a protocol that is offline. So if I, with secure cloud storage, I can send my data over now, go offline. The storage, the cloud server does the computation and comes back to me later. We can't really tell the difference between these two protocols. And availability kind of allows us to do that. Right. That's it. You can actually check out the compiler. It is for a research project fairly well engineered, and you can actually play around with it. I put way too much time into optimizing the Gradle build and stuff like that. So check it out. Yeah.
One, I think, kind of silly question. In terms of the cost modeling, so it seems like if I care all about network communication, for example, then I should always just, well, maybe I don't know, should. I could in principle always replace all the zero knowledge proofs with MPC. Or if I care a ton about network communication, then some of the MPC could be turned to zero knowledge proof. So is it like I give it knobs and I say I care, this much about network and this much about host communication, and that tells me what comes out.
Yes, actually, in our PLDI paper, we had two cost models built in. One was for local, like we call local or LAN computation, which said network is really cheap, and WAN where network is really expensive. But really, if you like, I imagine the proper way to integrate with a tool like this is to actually, because we're running on the Java virtual machine, you can really give your own classes. Like you can just give us a class for the cost estimator, or extend the class that we have and say, actually, I'm going to say the network communication is, really cheap or something.
Could you do it just in time? Could you, like, as it's running, like we see, oh, actually the network's really bad. Let's like switch from a PC to zero knowledge proof.
We did think about doing this dynamically, and there are a lot of advantages to doing it that way. Apart from just speed, but protocol selection right now is pretty expensive. We didn't try too hard to optimize it. We just use Z3 essentially to solve an integer linear problem. And for large programs, it will take a while. So doing it dynamically seems pretty difficult.
Awesome.
Yeah.
This work is so cool. It's really neat to see you be able to target so many different backends from the same source language. I'm really interested in the availability guarantees you mentioned as future work. I'd imagine that would target things like consensus protocols or as a way. If you need availability, that's where you would put it. Is that like in range or like fundamental obstacles to incorporating that?
I think that would be, Andrew has with Lanchan kind of integrated value policies to talk about quorum systems. So that work actually just does integrity and availability. And you can do very interesting things like specify, oh, I have like 5 hosts and I want availability as long as 3 of them are online. And I want as much integrity as you can give me with that. So that seems like the first target, like something that we can just incorporate into Viaduct. I don't know if that answers the question. But yeah.
I said one more like really just escaped my head when I said that. So just
Yeah.
So you say, okay, this is how this cost in the setting, but sometimes there's also a switching cost, right?
Yeah.
For example, it might be worse on a local level to stay in NPC, because I don't know, switch FHE or switching, but then when you add in the cost for switching, it's no longer worth doing it. Is that something that you consider as a cost model?
Yes, thank you for the question, because I completely glossed over it. That's part of communication cost. So actually one thing we do is we use ABY for our MPC backend, which provides 3 different types of MPC circuits. And actually we talk about the cost of switching between the circuits. So, certain operations are faster in an arithmetic circuit, others are faster in the Boolean circuit or YAO. But if you did that naively, then switching cost is really expensive. So you have to consider both. And there's also, cost of switching from, MPC to other things. Yes, that's part of communication cost.
But is it always actually, it's not actually part of the communication cost necessarily, right? There can also be computational switching costs.
Well, that's part of how we define execution cost and communication cost. Communicate like,
okay, so you just say that's
yeah. So, communication is actually very general with, if you're going from Alice's machine to Bob's machine, that's communication. If you're switching from MPC to something else, that's also communication.
Thank you. Next talking session is Fraser Brown from CMU on an infrastructure for building fibers. Oh.
I'm actually just gonna swing this. Okay. Ah. Can you hear me? Good. Okay. Fantastic. Fantastic. Let's make sure we can advance the slides. Yes, we can. Great. Cool. Well, thank you for basically the best setup for a talk I've ever had. That's amazing. So for some intuition for what I'm about to talk about here, you can basically think of us as a layer under Viaduct. So that's just keep that in your head as we move forward. And I'm giving this talk over my collaborator Alex's slides. He's giving a sort of shorter, more formal conference version later this week. So I encourage you to go check it out, ask questions, everything like that. Okay, so since this is a pretty PL friendly audience, I'll just go really quickly through why we need compilation in this area. And then we'll slow down a little bit to talk about why we built this compilation infrastructure. Okay, so I'm starting with the assertion that crypto systems, many crypto systems are computers. Is this better? Okay, yeah, I think there's just no way in the mask. All right, so starting with the assertion that many crypto systems are kind of like computers, at the end of the day, they're just executing some user-defined function, right? So let's take multi-party computation and say we have a big group of people and we want to figure out who has the most money without revealing how much everyone has. So to actually do that, what's really going on is everyone has to come together to compute some max function f. And that's just one example of a user-defined function, right? If we're in a zero-knowledge proof, maybe we want to show that we have some amount of money in our bank account that's non-zero. That greater than zero calculation is also an example of a user-defined function. Ditto, if we're doing image recognition over some secret data, that cat recognition algorithm there is just some function. And there's a ton of new work on computational crypto systems. And importantly, the functionality and performance of the whole crypto system sort of depends on F. F and the way F is expressed is actually pretty important. So the issue for users is that crypto systems operate on very, very low level representations and encodings of F. So this is just like a 4-bit comparison. It's really gnarly. So imagine doing anything more complicated than that, right? So if we want to make it easier or even possible for people to use these new exciting crypto systems, we have to address some high level problems related to this underlying function here and how to express it. First question, what do we actually do, right? If we're trying to piece together larger computations from low level functionality, it's going to break down at some point, right? We don't write web browsers in assembly. Similarly, not going to fly here. The second question gets back to performance. How do we optimize F, right? And this is especially important because a lot of these new crypto systems are sort of still on the border of practicality, right? We don't see a ton of commercial deployments of FHE or ZK proofs, though I guess the last one is changing a bit in the blockchain area. So in a way, these questions boil down to how do we generate low-level, high-performance code from some high-level representation, right? And surprising absolutely no one, the answer here is compilation. We've been doing that for a really, really long time. Crypto systems need compilers. And there are actually a bunch of different compilers in this space already. That slide comes out weird on the projector. Oh well. And they do a lot of things very, very well. So I can't get into all the details here, or we'd be doing 10, 30-minute talks. They make a lot of things possible that weren't possible before. But they also have some drawbacks, and not typically in the more research side of things, but maybe more on the engineering side of things. So for the most part, this is just a generalization. The research compilers are a little bit incomplete, a little less generalized support than we might hope for if we were deploying them in the real world. And then on the other hand, those industrial compilers in orange are quite complete and robust, but they operate on really, really low level languages. We're talking hardware description languages, or you don't get if statements. So it's really hard to do anything useful. And these drawbacks here aren't because these people or anyone who's trying to do this is bad at building compilers. It's because compilers are really hard to build, really, really hard to build. Which brings us to the motivating question of the talk. How can we make it easier to build compilers by using shared infrastructure, maybe for these representations on the side of the slide, maybe even beyond that? So is it possible to use shared infrastructure for cryptographic compilation? Shared infrastructure is fantastic, right? Because it saves a bunch of time. So I mostly live in non-crypto world. And when I want to play with a new optimization or write a new checker or even design a mini language, I just pull out my LVM docs and like LVM libraries. It's very, very easy. I don't have to build a whole compiler or optimization pipeline from scratch. The second benefit is that shared infrastructure generally produces better compilers. The compilers get tested and just used more frequently. And since pieces of infrastructure are shared across front ends and back ends, you only got to fix bugs once. That's a lot more efficient in general. So this talk presents our approach to and implementation of shared compilation infrastructure for crypto systems. And first, we'll talk about our compiler infrastructure, Circe's design, and also kind of strange computational model. And then we'll talk about the performance of its output. We'll move on to how to use Circe to build a new compiler. And then finally, we'll talk about combining different backends in order to do new things. And normally I would keep this mysterious, but we sort of saw an example of how to combine backends to do new things before. So that's the sort of thing to keep in mind for that fourth bullet. Okay, so with that, let's kick it off with the design and computational model. To do that, we have to go back to that low-level representation of F and understand it a little better. And for all the crypto systems we've discussed so far, F is actually represented as some kind of circuit. And we're going to narrow in on zero-knowledge proofs now and say that F is an arithmetic circuit. So that's a directed acyclic graph with inputs, outputs, wires, or inputs, wires, and gates. What's on the slide? What's on the slide is what's in the circuit. The colors match up. It's all very beautiful. Alex did a great job. And the domain of the circuit is finite fields. Wires indicate field values. Gates indicate field operations. So up here, we have a field multiply of x sub 0 and x sub 1, and then that output is going to this field addition here. In zero-knowledge proofs, you get optional equality assertions. And maybe the most important point, fewer gates typically means better performance. That's true in zero-knowledge proofs, generally true in other applications too. So let's go back to our motivating ZK application. We're asking this, do I have more than $0 question for a zero-knowledge proof? And the question is, how do we go from that computation on the left to the circuit on the right-hand side? Or really, how do we go from any arbitrary computation on the left to the circuit? And it turns out it's a really huge pain to do this. We're reassigning X there. You can't do that in a circuit. There are no if statements. You can't have that for loop. It's going to take a lot of different steps to do this translation. We're going to eliminate variable mutations. So instead of reassigning X, we're going to have little versions, kind of like putting something in static single assignment form. There's also no such thing as conditional branches. So we're going to have to guard these assignments with that if condition, but y greater than 0. Similarly, no looping, right? You have to unroll loops up to some user-defined, perhaps bound, or maybe the compiler does some static analysis to get the bound. Doesn't matter where it comes from, you have to unroll the loops somehow. There's more than that. There's this kind of whole list of things. And what's really interesting to me is all of those things are really, really similar to what you have to do in bounded model checking. And this is actually fantastic news, right? Because as a community, we've been thinking about how to do bounded model checking for a really long time, like decades and decades, way longer than we've even thought it was possible to, well, longer than we've known about zero-knowledge proofs, I think, actually. Yeah, thank you, Riyadh, for the thumbs up on the date there. So I'm going to do a really quick model checking primer, which is, I guess, probably explaining something you already know, but I'm going to push on for the more crypto-inclined people. So bounded model checking is a way of proving properties of programs, saying things like, hey, my program is memory safe, or it conforms to some specification. And in part, the way model checking works is through compilation. The inputs are this program on the left and the query on the right, something like, is there an out of bounds access in my program? And then crucially, a compiler is going to compile the program and the query down to a logical formula, something like A or not B, or whatever. But the important thing here is that is a circuit-like representation too. There's no branching, there's no looping, there's no reassignment. This is our circuit-like form. So once that's done, the checker is going to feed the logical formula to some kind of solver that tries to determine a satisfying assignment. Wow, you have to be really close to this microphone to get it to pick anything up. Some assignment of all variables in the formula that makes the whole formula evaluate to true. So for example, if the solver comes back with an answer for this access out of bounds query, that means an out of bounds access is possible in the program. If it doesn't, that means no such access. So the key point here is that SMT formulas for solvers are a circuit-like representation. Very, very, very similar to the representations for zero-knowledge proofs and FHE and MPC. And we call this model in the paper an existentially quantified circuit. The circuit part encodes that the representation is mutation and control flow free and of fixed size. And the existentially quantified part means different things in different backends. So in a zero-knowledge proof, there are variables who are known only to the prover, whose values are known only to the prover. FHE and MPC have their own models. And in SMT, these variables are actually just existentially quantified, right? There exists some variable, and the solver is going to search for an assignment to that variable that makes the whole formula true, like we talked about before. So given this regime, our infrastructure, CERC's job is to generate existentially quantified circuit representations for things like SMT and zero-knowledge proofs from high-level languages, kind of like model checking infrastructure with a bunch more backends. And the core of CERC is this intermediate representation, an abstraction of an EQC that's based on the SMT-lib standard. So it provides a rich set of types like bit vectors and tuples and stuff, but note that it is a circuit-like representation. You know, there's no control flow, there's no mutable state. Compiler developers support new front ends new languages by attaching front ends for those languages to CERC's IR. They also support new backends by lowering from CERC's IR to representations for each potential system. So maybe an arithmetic circuit-like format called R1CS for zero-knowledge proofs, or just straight up SMT-lib for an SMT solver. And in general, adding a front end to CERC is much harder than adding a back end, right? Because the front end has a different computational model, while the IR and the back ends all share this EQC thing. So to make this easier, we created this library called Cercify that really helps manage the tough parts about going from a traditional programming model to an EQC. So it's going to help manage variable scoping and loop unrolling, stateful updates, things like this. And Cercify will handle most of that automatically. We'll show an example later in the talk. CERC also provides a bunch of optimization passes, standard things like constant folding, or more system-specific optimizations like linear scans. And this is the bird's eye view of the whole architecture, no pop-ups. If that reminds you of LLVM, that's fantastic. I really, really should. Just like LLVM, over there you see front ends for different languages like C and Rust. You attach new front ends to LLVM by translating from those front ends to LLVM IR. You add support for new processors by lowering. Oh, do you have a question?
Yes.
Yay.
I was just wondering, so DKP and MPC, like some of these actually they require different backends. So like for instance, if I were to compile to DKP, I don't need ability memory abstraction. But if I were to compile to MPC, I need ability memory abstraction in the intermediate representation. So like in this sense, is it okay to just have a single intermediate representation for all of them? Like how can you make sure like when I want to compile to MPC, it actually has that ability memory?
Yeah, that's a great question. So we have an IR that's somewhat extensible. So we had to add a few different constructs when we were making our MPC backend. We started with zero knowledge proofs actually. So we baked in prime fields from the beginning. That's not in the SMT-lib standard. So we sort of add little pieces to it, but we're really taking the core like circuit-like abstraction from SMT-lib and then adding little pieces of information. Like we also need knowledge labels for some of the other backends, which we don't in zero knowledge proofs. Cool. Any other questions while we're at the pause point?
MPC and FAQ still work in progress?
Yeah, so MPC, you can like go to the GitHub now and use it. It works. FHE is really baby. ILP, go ahead. That's pretty mature. Actually, if you're interested in using an ILP solver for any of the protocol assignment stuff, that could be fun. We actually have been recently using it to do protocol assignment for MPC.
Just curious, why in FHE, why didn't you do HE-lib or LSA?
Honestly, because we've just started with it and we probably don't really know what we're doing.
And then just to clarify, for my question, I'm still confused. If you did like when I compiled the search and IR, I should already have an idea of the backend, like because then I have to decide whether I want to let you use the extension of the framework or not. Right?
Yeah, so that's a great question. There's sort of two concerns going on here. The first is what's in the IR, and that's always the same. Like we extend the IR a little bit for applications like MPC, say these knowledge labels, those are always in the IR. But if you want to do, you can turn off and on different optimization passes that operate over the IR. So there's some things that we only use for the zero knowledge proof backend, right, that make no sense for the SMT backend. There are also, interestingly, a bunch of optimizations that like help SMT get faster and help zero knowledge proofs get smaller. So that's kind of a fun thing. But yeah, you can toggle the optimizations on and off. Anyone else? Cool. Okay. So we were doing this sort of drawn out LLVM analogy here. So the pipeline with LLVM, like compared to LLVM, is basically the same. The real difference here is that IR. The LLVM IR is kind of an abstraction of a machine, right? We're an abstraction of a circuit. And just like in LLVM IR, you know, people sort of get together and decide, okay, we're gonna add a new instruction to LLVM IR or like add a new type or something. Similarly, we have to go back and do that sometimes too in SERC IR like we were just discussing. Okay, so in the rest of the talk, I'm gonna be going through some SERC compilers for proofs and for SMT. And now I think we've mostly gone over this, but we also support these backends. This one, not very good. You can use this one, you can use this one, but we're not going to cover those today. Yeah.
What's the little hammer? What's the difference between this one with the little hammer and the one without it?
This one is like fully evaluated and presented in the paper, and these ones are not in the paper, so they have the little hammer. Alex did this all over. He has these like little pictures next to all the boxes. It's very creative. Cool. Okay, so we're going to talk about performance and how are we doing on time? Okay, I'm going to speed through performance. First, setting the stage. In this case study, Alex built a compiler for the Socrates language. That's an industry language for writing blockchainy zero knowledge proofs. That's some Socrates code, looks pretty normal. Its basic types include fields and then everything you would expect. It's got great tooling. It's supported by the Ethereum Foundation. You can do normal looking things like importing and making functions and manipulating arrays. So the Socrates compiler is quite big. It's 28,000 lines of code. That's minus the parsing, the tooling, everything else. And it's actively being used at a few different places in industry. So a lot of people spent a lot of time on it, and it does a pretty good job. Like its output performs well. You're surprised if it's wrong. Does not crash much. So we tried to recreate the Socrates compiler using SERC. We already had the SERC infrastructure with the SMT, ZKP, and ILP backends. We just attached a Socrates front end. It took us about 700 lines of code. And it was really, really easy. And that's not because like we're great at building compilers, it's because we were building on shared infrastructure, right? That's the difference between like go write a Rust compiler and go write a Rust front end for LVM. One of those is like a lot easier than the other. The Circe version also matches or outperforms Socrates on all their standard library benchmarks, with the exception of that like mustard one that's circled right there. Full benchmarks are in the appendix. We also compared Circe-derived compilers to other zero-knowledge proof compilers. The Pekin numbers are like slightly skewed. They're from their paper benchmarks, but they have a lot of small arrays, and we support this small array optimization that they don't. So it looks like it's really bad, but it's actually not. We're basically at par with them. Okay, so now we're going to try to tear through how you actually build a front end for a Circe compiler. And the key point is that we're not going to make you do all of that state management stuff we talked about before that's such a pain. You're not going to have to just manually do all that yourself. That's where Circify is really helpful. So there are three key steps to using this library. First, you have to tell Circe-IR how to represent the values in your language. Then you have to define a couple more functions that just kind of hook you up to Circify. And finally, you translate your AST to Circe-IR by building essentially an interpreter. So we're going to do this for Socrates with just one AST node. So representing Socrates language values in Circe-IR is really easy. The types are basically the same. We're going to ignore that. And next, we have to hook into Circify by telling it how to merge states at join points in a program. So what I mean is it automatically has to, when it's getting rid of these branches, resolve control flow, right? So like, what is X? If on one branch it's Y, and on one branch it's X. It's pretty straightforward here. It's just, okay, if B is greater than 0, then it's Y, otherwise it's X, just your standard sort of guarding. So once Circe knows how to do this, anytime it hits a join point, it's just going to do this operation. You can go on and build your AST interpreter. So all you have to do conceptually is write this interpreter for your AST. And I know this is a ton of code. I could not figure out how to edit it. So just look at the things that are being pointed to. So we're going to match on AST nodes up here. And this particular one is for the constant bounded loop case, something like, from 0 to 5, we're in a loop. And first, we're going to use Circify's enter scope function to automatically enter a new lexical scope. We'll declare and initialize a new variable for the loop increment, something like I, right, from 0 to 5. So we have I. And we're going to use Circify's declare init function. And after we do that, Circe will automatically handle all the variable versioning for us. For each iteration of the loop we interpret, we're going to push a new lexical scope with that enter scope. We're going to assign a new value to the iteration variable I using Circe's assign function. That automatically takes care of versioning. Then all we have to do is interpret every statement within the loop. Behind the scenes, Circe is going to be managing all the guarding. If we have multiple if statements happening in the loop or all the variable versioning, that gets taken care of for us. Okay, what time am I supposed to be?
12:15.
Okay. Okay. So we're going to talk about some crossover opportunities, and you have a lot of like fancier intuition from this. Actually, from Viaduct, the things we're doing here are way more simple than like figuring out what should be a ZKP or an MPC. So this is my favorite topic though, because it doesn't really have an analog in traditional compilers, right? Like on the left, on the right, on the left, you see LVM, and like there are all these backends, but they basically do the same thing, right? They just execute code. So there aren't so many interesting applications you can get by just like combining those backends together. In contrast, like zero knowledge proofs and SMT solvers and ILP solvers all do really, really different things. So you can sort of combine them together really easily because of the shared infrastructure of the compiler. The first application I'm going to talk about is zero knowledge bug bounties. And I have a little bit of a problem with this one from a practicality perspective, especially as I'm presenting it here. I'm happy to talk about that offline, just small caveat I'm forced to give. But it's a very cool demonstration of this system. So in the bug bounty scenario, a code base owner publishes some code, and let's say in this case, some assertions about the code, about its correctness, like, okay, these are the invariants that should hold. Then some bug friend person like me comes along and is like, okay, you violated your invariant here and here and here. Now we have an incentives problem, right? Because now the code base owner knows about the bug, but they don't have to like pay me a bug bounty, right? They already have the bug. They could just leave and do nothing. I have to say I've never had that experience in my life, but I think especially if you're doing sketchier things, that can actually happen. So, okay, what we actually want to do, what many people have proposed as a really interesting like way of addressing this issue is zero knowledge proofs of bug. Prove there's a bug without revealing what it is. And then when everyone's satisfied that the bug is really there, we're going to do some simultaneous exchange of bug details and money. So we built a proof of concept pipeline that can help automatically find bugs and then automatically prove them in zero knowledge. First, the bug finder compiles the code and the assertions to an SMT formula using Cersei. They also provide some hints, little like facts about the code or the bugs they're trying to find that allow the solver to actually find the bug, right? Because just feeding massive pieces of code to an SMT solver and being like, go crazy does not work very well. So you have to sort of nudge it in the right direction. Happy to talk more about that offline too. So let's say the bug finder gets lucky and those hints worked and the solver is indeed able to find a real bug. Now, Cersei generates a zero knowledge proof of the bug to send to the codebase owner. Once the codebase owner is satisfied by that proof, there's some sort of simultaneous bug reveal and payment thing. We didn't do that. That's someone else does that. And everyone goes home happy. So we demonstrated this proof of bug pipeline on this OpenSSL CVE that we didn't find. That was a pre-existing thing. And the cool thing here is not that we made it possible to do this, right? You could like take an SMT solver off the shelf and then take a zero knowledge proof system and like wire them together and make something happen. The cool thing is that it was really, 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 really easy because everyone lives in the same infrastructure. So you could just, 60 lines of code, off we go. You can do the same thing with optimization. So we used the solver to figure out how many loop unrollings we needed to do when we were compiling for zero knowledge proof. I'm not going to go into that in too much detail. It's pretty straightforward. Boom. You figure out, okay, it's not satisfiable. In that case, that means 32 unrollings was right. Off we go. We have our final computation and we send it to the zero knowledge proof backend. Okay. So that is it for, oh yeah.
I have a question about the that example was very interesting. I just wonder what stability is being included because the stability involved like a machine model.
Oh no. We are not fancy like that. No, we just we like have C code and we're saying, okay, like we have semantics of our C code. That's what the SMT is reasoning about. This is not a fancy proof of bug pipeline. This is just, we were able to find the bug, boom, press a button, automatically it becomes zero knowledge proof.
Well, I guess it depends on what kind of bug you have, right? Like
Very
memory
much.
overflow bug, that require like some kind of memory model. That's our machine model.
This actually is an overflow bug. So I guess in that sense, I more meant like if you're trying to deal with architectures, well, I guess we deal with the architecture specific details of the version of C we model. So I think we're doing, in that case, like 64-bit, I can double check. So we have that level of machine model, but we aren't modeling like really fancy features of the underlying architecture, right? We have model for integer semantics, but not for like what's happening in the processor.
I think there is a simple machine model.
Yeah. And the thing that would be hard actually that your question gets at that's really interesting is, let's say we wanted to prove facts about bugs that had to do with like the RAM register model of this machine, say, then things get a little hairy, right? Because we've gone to our circuits. So now we have to think about like, I guess we'd have to add a totally different front end. We couldn't use the C front end. It would have to be like an x86 front end, and then we'd have to have a shim over it. It would get really complicated for some kinds of bugs, which is very interesting.
So is there a simple statement to express like this program has a memory overflow? I just wonder what the statement is like. You know which definition you want.
Yeah, you can basically, like, if you have a sense of what size your integers are, you can just have assertions around like every arithmetic operation to check if you've overflowed. And actually SMTlib does, it like provides some overflow checking primitives like in the library, which is kind of cool. So you can sort of build overflow semantics from that.
It's a complicated thing.
Yeah, actually, I mean, it's more complicated than it could be. It could get more complicated to the point where using Cersei would be hard. But you can do a lot of very expressive, like I would say I've done like a lot of bug finding verification-y stuff. Other than the floating point, you could do everything in Cersei too. So that's like browser bugs, C++, C, that sort of semantics. Okay. Whoops. Sorry. Yeah, okay, there was like a wrap-up slide, but we don't have it anymore. You can find the link to the code in our paper. Check us out. If you want to build a compiler for one of these crypto systems, please come talk to us. We'll help. If you're interested in optimization, yeah, send an email. Awesome, cool.
Okay, let's get started. Our next talk is by Korean. He has done a lot of very nice work on formal verification of crypto, and he's going to talk about one of his works today.
Thank you. So, I mean, this is mostly based on two papers with these co-authors, and everything I'm going to talk about is available online at this Git URL, and the work is based on the 2019 and 2021 CCS papers. So, I mean, just to clarify things, this is not going to be about any new cryptographic protocols, neither about universal composability. We've heard enough about that, and I think it's a very important problem, and I'm glad to hear about this, but it's also not about finding security proofs or even protocols, which is also another interesting topic. But what this is about, this line of work was about, basically several years ago when we started this at 2018, I always heard in the crypto community that all formal verification is just for toy problems, protocols in cryptography are complex, and basically to prove that this is not correct, the only way to do it was to have a constructive proof of very complex object. So I'm going to talk about why we chose MPC, and then later on continue to zero knowledge. And obviously you can say that there's room for work with other objects, but I think MPC and zero knowledge to me are among the sort of more challenging. They're not the low end key establishment or key distribution simple protocols. They involve a lot. And also, that's a personal point of view, is once you've gone through the work of formally verifying such protocols, might as well do the 20-30% extra work to get formally verified executable software from it, because there's still going to be a gap between what did you actually verify and what gets executed in the real world. So, I mean, with this audience, you all know MPC at this point, probably. I'm just going to stress about the security models. I'm going to stress that, typically when you design these protocols, obviously the easy one is to work in the semi-honest or passive, but the more interesting one is the malicious or active. And the reason why I'm stressing about that, because a lot of the time, the early formal verification work didn't really address the active cases. And what's interesting when you actually work in MPC, which I've done for now the last 10 years, you look at some of the most fundamental protocols like BGW, seminal protocol. There's actually not a full proof till like from 88 till 2011. There wasn't a full proof till these Asheroff and Lindell wrote an 84-page paper. And then even when you look at that paper, it's fantastic. But when you start to get into universal composability and active security, it leaves a lot to be desired. I mean, there's still a lot. If you come like at SRI here, the group that does formal methods, which that's how I got introduced to this field. I mean, their level of what the proof means is very different than what you see sometimes in cryptography. And to me, trying to bridge these two worlds was trying to bring that trigger even there. But anyway, we started this work by looking at something as fundamental as BGW and optimizations of it, and trying to really formalize as much of it as we can and get executable software from that. And then a natural question is like, why MPC? I quickly glanced through this. Is one, it's theoretically mature, very well understood. It's starting to make its way into the real world and blockchains, and there's a lot of companies at this point. It's a complex protocol. In some sense, it's crypto complete, right? Any interactive function securely can be evaluated using MPC. And when you start looking into dynamic groups or new, stronger security models like proactive security, when you have long executions and you have corruptions that might surpass the threshold, these protocols start to be pretty complex. You start to have 6 or 7 sub-protocols, and you have commitments involved and all this. So using it as a representative of what you can actually formally verify and synthesize, I think to us, when we started, was a good benchmark. And again, for some of the most fundamental protocols were not completely written even on paper, the proofs for decades. Obviously, I don't need to tell you how hard it is to get these complex protocols right. The literature, there's a lot of examples in the literature where simpler protocols, just Byzantine agreement, had issues in them, even though they had proofs on paper and were peer reviewed. And it took sometimes years to find those out. So imagine something like MPC that involves not only correctness or it involves secrecy and privacy and against active adversaries. So that was also another reason to look at it. Anyway, so EasyCrypt, most of you know about it. It's an interactive theorem prover tailored for cryptography. I'm not going to go through this, but the most interesting thing is in the logic that they have is the random sampling operator, and the fact that you can use this one notion of modules to represent security notion, adversaries, and different things. It has an imperative language that it's very powerful. So we basically stuck to EasyCrypt. An interesting thing, when we started doing this work, actually back in 2018, we did look at F-star. And for a moment there was like, should we try to do that level of work in F-star, and very quickly realized that to have done something like this in F-star, I mean, again, this was started 4 years ago, would have been much more difficult. So when you look at in EasyCrypt, how do you define something like El-Gamal? For those of you who haven't seen it, it's the El-Gamal encryption scheme. It's as you would expect it. You have, again, this random operator which samples from a probability distribution is very important when you try to do your proof of proving indistinguishability, for instance. So here, for instance, the key generation, you're simply saying that I have a prime Q, and you're going to sample randomly a secret key from 0 to Q minus 1. And what you return is basically the secret key and the public key, which is D to the X. And then when you encrypt its message M, you're simply just blinding it with the public key raised to Y. So EasyCrypt allows you to do all of this, which if you had to do this another theorem prover, look, SRI has its own theorem prover. PBS has been developed for years, been used in a lot of fault tolerant systems, but not the proofs being done there don't have the kind of sort of indistinguishability and game hopping that we see in cryptography. So back then, having to replicate all this would have been an enormous amount of work. So that's why we went with EasyCrypt. Anyway, so what is our work exactly? So what we have in these papers and what we did is to do the abstract definitions of all the basic primitives that you would need to do something like MPC and zero knowledge. So we're talking about starting from all the way from basic secret sharing, linear secret sharing, verifiable secret sharing, commitments, what a protocol is, MPC protocols, proactive MPC. Then once you have these definitions of these protocols, you need to do security definitions. These are like game-based security definitions for indistinguishability, for unforgeability, for commitment, like for all the different primitives. Once you do this at the abstract level, that dotted line highlights basically the difference. Everything on top is the abstract level. You do composition proofs between these different abstractions. So for instance, if you want a functionality that's called proactive security, you need to compose an abstract protocol that would give you re-randomization functionality versus a deterministic functionality. And then once you've done all this, you do this once, you prove composition theorems between these, and these are not universally composable. This is mainly sequential composition. Then when you actually instantiate every algorithm as a concrete scheme, so like for secret sharing, you can have additive secret sharing or Shamir secret sharing or anything else. You need to prove basically equivalence between the instantiation and the abstract definition, and then you inherit all the abstract composition theorem. So we've done this for secret sharing, MPC, zero knowledge, and then MPC in the head, which is a way to get zero knowledge proofs if you have an MPC protocol. And then once we have the concrete instantiation of all these primitives, you can extract executable code automatically. And that's what we did. So to put this first part of the work in context, till we published that paper, so you had some efforts of trying to formally verify MPC protocols, but they were mostly in the passive, considering passive adversaries. They didn't extract executables except for the two-party case. And they did not really have proactive security nor active, like proofs for active adversaries, but we only dealt with static active in EasyCrypt. So this paper from HK plus 18, they had, what they proved really in that paper is that if you have a protocol that has certain properties, there exists a simulator, and they did that part by hand. And they didn't for active attacks. They didn't do it in EasyCrypt. You want everything to be fully verified in EasyCrypt. So that was a big part of it. So in that paper, when you look at it, what we did at the abstract level for secret sharing, so we proved the semi-honest or passive basically version of security that a secret sharing would give you. Then to get security against active attacks, you have to add commitments. So we have the notion of commitments and then Peterson commitments. Then you get from that verifiable secret sharing, and now you can start talking about maliciously secure MPC. Quickly, the way it looks in, it's not far from another programming language. I know there's a barrier to EasyCrypt, but if you've done OCaml or other programming languages, if you understand the notions of game-based security and the crypto, in my experience, the barrier was for people like my colleagues who are like PL experts, been doing formal methods for years. Sometimes explaining the way we do proofs in crypto is a little bit challenging, especially the game-based one and the indistinguishability, and then reducing to a hardness assumption. But I mean, luckily we did that once. I mean, everybody can hopefully build on it. And then for verifiable secret sharing, you can also then build on top of the standard secret sharing. Yes.
So I just have a question about this verifiable secret sharing. I guess like to prove the privacy, there's like you need a bunch of number theoretic assumptions. Do you prove all of those from scratch?
No, we assume these. Like discrete log, you say it's no. Discrete log.
That's an assumption. But
yes.
This, like secret sharing itself, you don't need an assumption. You can prove.
No, secret sharing we do prove. Yes. So we had a library for polynomials. We do a library for polynomials, and the way you do the proof, you give the algorithm the randomness, and then you prove correctness. And if the
but I guess I'm asking, like, for instance, did you prove, like, for instance, that the elements have an inverse? I think there's a bunch of low level numbers.
No, we did not. That the elements, no. Okay, so that's actually something in the future work I'm saying. When we even extract code, we rely on the libraries of OCaml that do the fields and operations over groups and fields. That part we didn't do, but we did implement in EasyCrypt a library for interpolating polynomials, or if you want to do at some point, the Berle-Camp-Welch for active security, that we did implement, but number theory, no, we did not. It's a good question. So then, I mean, there were also commitment schemes. All this is in the open source. So then one of the interesting parts was how do you define MPC back then, EasyCrypt? So you define it basically through phases. So you have the initial phases where you will basically secret share the inputs. And then we have the next phase. It's like, if you've seen that before in papers, like the next message in when you define protocols. So we had that notion. And then the finish phase is basically to distinguish because we wanted to be able to capture proactive security, and in proactive security, you would compose multiple sub-protocols in there, and then you have the output phase where you actually then reconstruct and open everything. What we didn't do here is what's called reactive functionality, so functionality that would keep running forever and maybe take some other input that is not the first secret shared values. And then for the abstract level, for MPC, we show basically that if you have deterministic functionality doing MPC, and by deterministic meaning that you have a circuit that's deterministic and you can compute it on inputs, and you always are going to stick with the same shares. In proactive, you need to re-randomize the shares so that you can hold the same secret, but you throw away the old secret. So that's required what we call a random functionality. Then we proved there that if you compose these two, you would get the proactive functionality, so that over time, if you have an adversary collecting all the shares from different epochs and you're throwing away the old ones, you still are secure. So, I mean, it sounds pretty trivial to do on paper, and it is, but when you have to do it in EasyCrypt and have it verify, it was quite an undertaking, actually. Yes.
So is the fact that it's an undertaking in EasyCrypt, is that exposing something important, or you see what I'm saying?
Yes, I see what you're saying. I mean, we're recording this, but I think I don't think EasyCrypt is the end all be all. I think, I mean, it's a massive project. It's still not as natural for somebody who has designed algorithms to actually work in EasyCrypt. And as a matter of fact, Vito, my colleague, he's the one that has all the knowledge in EasyCrypt. This would not have been possible without his like 6-7 years of experience there. If I was to do it as somebody who has designed protocols, I would. Some of the things you have to do that are very counterintuitive, and you have to sometimes adjust the way you model things. I don't know what the answer is, but
there's room for better tools.
Yeah, oh, definitely, absolutely. I don't know what the better tools are, but I mean, especially, I mean, I think you have what Andrew mentioned at the beginning, you have to start with something that considers UC. I think that's the part that retrofitting EasyCrypt to CUC, and I saw the talks is, I mean, they're doing it now, but I don't know how easy it is. Now, I'm wondering if you started from something that is universally composable and takes into account these complex notions, if things would have been easier to do. I don't know. And I know, like, for instance, also now talking about lattices and post-quantum schemes, I have not looked at that line of work, but I don't know how easy that line of work in EasyCrypt will be. Okay, then so this was abstract definitions, and then you actually implement each protocol. You can choose to prove as much as you want. I mean, you can prove all the number theoretic assumptions you want, but that's like going too much. At some point, we had to assume certain things, and then you have to write your whole proof. And again, EasyCrypt is not going to find the proof for you. It can help try automate some steps, but at the end of the day, you have to know the exact security game, like in pen and paper proofs that you want to prove, and you have to be basically able to write the proof to show distinguishability and reducing it either to an assumption you had, or it becomes like a statistical indistinguishability and obvious. So I'm going to skip through that. So again, for MPC part and also the following one, it's all online. As you can see, there's a lot of modules and definitions. These are all EasyCrypt files. And the point is that hopefully we've done this once, and then if there could be some mistakes, but people can reuse it and build on it. And hopefully over time, actually, if there's anything that we missed, it would be captured. Because, yeah, I mean, when you, in the papers are great, but sometimes I wonder how many people have really looked on the proofs and in the appendix and simulators, and mistakes happen. Typos, some of our typos easy to fix, but some are more involved. Okay, so once you have the EasyCrypt specification of primitives and algorithms, what we noticed is that actually the language is EasyCrypt is very close to YML. And YML has a massive framework that has a lot of tools. And what we noticed back then is, I mean, there was also ongoing work to try to extract from YML, extract OCaml in a verified way. So the way we're getting the executable code is from the EasyCrypt files, which you've seen some of the examples. we basically wrote a translator that extracts YML, and from YML, this translation is pretty straightforward. You can go to Y3 and there's a verified tool that extracts OCaml from Y3. Now from Y3, can you get C or maybe go to a language like that of PVS, which is SRI Interactive Theorem Prover? The answer is yes. We haven't done it yet. And as a matter of fact, actually, PVS extracts C, not in a verifiable way yet, but so suspecting that going to PVS and then C might be more interesting because you can do a lot of other things in PVS, like we're not reasoning about memory safety, runtime, things like that. I mean, these are not things you actually look at in EasyCrypt. EasyCrypt is more focused on correctness and the cryptographic properties. So when we started this, like, okay, how bad will the performance of this extracted code be? So what we did in the first paper is take something like Charm, which is a Python-based framework that has a lot of cryptographic primitives, secret sharing, and you can use to implement MPC, and compare like very basic building block algorithms. So you have basically in Charm, if you were to implement secret sharing, they have actually an implementation of secret sharing. How much time it took to share and reconstruct for 5 or 15 parties. And we initially thought that it's going to be an order of magnitude overhead. Sorry. And the answer, what we found out that it depends, because when you share, it was a lot of overhead because here we extracted our own library of polynomials. Because when you share, you have to construct a polynomial and then evaluate at different point. So we implemented that in EasyCrypt, and that's what we actually extracted and executed. Now, if you were to replace that by an OCaml native one, I mean, the problem is you can have a security issue there, but you'll get some speed up. The reconstruction, on the other hand, was not that far off, like 2x or 3x. So that was encouraging. And when you look at the commitments, for instance, different field sizes, again, similar performance. It was at most an order of magnitude, not 2 or 3, which initially we were worried that that's going to be the case. So what we didn't do in that first work was, as I mentioned, UC-based proofs of BGW, which is going to be a lot of work. Underlying broadcasts. I am not aware actually of anybody who implements MPC in the real world on top of broadcast. That would be something, if you really want to stick to the theory, that's what you ought to do. Nobody does that. They do pairwise channels. And that's what we did in the actual executable. Now, if once we would have a underlying broadcast, or actually broadcast and consensus, I mean, there's intimate relations and there's multiple protocols, right? So, I mean, which ones do you actually verify? That's a very interesting open issue. Actually, Elaine, to your point, verifying the underlying implementations of groups and fields and in some of these number theoretic notions, we didn't do that. And then comparing against something like Scale Mamba or AMP, where people have really spent a lot of time. It's a little bit of an unfair comparison because of a couple of things. One, you look at these implementations, people are doing a lot of parallelism, which we did not. We're actually starting to look into that in another context, the context of zero knowledge, and it should be doable. The question becomes then, like, if you get another order of magnitude improvement, are you now comparable enough to all these manually implemented versions that have a lot of optimizations manually into them? And then I think translation to C or other languages, even Rust, would be very interesting. Oops, sorry. I clicked on, okay. All right, so the second part is once we had MPC, an interesting realization, I wasn't sure initially if this audience knows zero knowledge or not. So this is well known for now several years that you can get, there's an intimate connection between zero knowledge and MPC using this MPC and the head framework, right? So the notion of a proof, traditionally, it's a statement you would verify cryptographically, was basically generalized to be an interaction between a prover and a verifier, and we can have a statistical or computational notion of the security there. Long story short, in this part, I'm assuming you know what zero knowledge is. Since 2000, this seminal paper by Shai, Grushelowitz, Ostrovsky, and Sahai, they basically say if you have an MPC protocol that can evaluate a certain I mean, MPC protocols are generic. You can evaluate any arithmetic or binary circuit. You can use that to construct a zero knowledge proof system that is generic for any relation. And what you do is simply, you have the prover taking that MPC protocol. And the good thing is about you need the MPC protocol to only be honest, again, it's like secure against honest but curious or passive. I mean, there's a trade-off between the complexity if you have an actively secure MPC protocol, but for now, semi-honest or passive is enough. What you would do is the prover will take the statement they want to prove and express it as a multi-party relation, emulate as if there's a distributed set of parties doing the computation, but emulate it all in their head. Basically, like if this is a server, 3 processes, and you do all the coin flips locally, and then you commit to the views between the parties, the messages the parties send to each other. The verifier will flip some random coins and challenge you to open some of these views, reveal all the randomness and all the commitments. And if when you open those check and the relation, basically the output of the computation, the MPC was 1, then you actually know that the prover had a witness that satisfied this. Okay, so this uses here MPC as just a black box. Once you have a MPC protocol that was verified, you can then use that as a black box to build a zero knowledge proof that is also verified using MPC in the head. And that's basically what we did. Again, we had the BGW version from before, but then what we did in that second paper, which was last year in CCS, is we looked at another MPC protocol that's based on additive secret sharing. This is a paper from like 20 years ago almost by Uli Maurer. He actually wrote it as a way to teach MPC. It's a very simple protocol, very basic arithmetic. But the cool thing about that protocol is that it, for a very small number of party 3, it's actually pretty efficient. And it's not only that it's efficient, it works for what's called general adversary structure. Like typically in a lot of the literature, you'll see it saying if only up to 1/3 or 1/2 of the parties are corrupt, then you're secure. General adversary structure allow you to express something more complex. You can say as long as this party is not corrupted, but everybody else, or as long as certain basically sets, you start to express who you can protect against or who can recover the secrets as a set, then you can do the computation with holding the security with these notion of sets. So for 3 parties, it's actually pretty straightforward. And what we ended up doing is taking our MPC protocol definitions and security definition abstract ones, extending them to the notion of MPC in the head. We defined zero knowledge as a notion and its correctness, soundness, and a zero knowledge protocol, and then did all the definitions at the abstract level to show how you would compose MPC with whatever other primitives you would, like secret sharing and MPC, to get a zero knowledge protocol using MPC in the head. And then we have 2 implementations, one based on the original BGW synthesized MPC protocol, but then we also implemented Maurer, but Maurer, we implement, like there was some part of the team implemented in Jasmine, which is a lower level language that also gives you like verification guarantees, and there you are actually a much lower level, so you have much better performance than OCaml. So when you look at this, we experimented with different prime sizes, like small primes and large primes, and measuring the number of circuit gates you can deal with. I mean, this is already outdated at this point. We can even do an order of magnitude more. And it's not bad. It's not comparable to the latest and greatest zero knowledge implementations based on MPC in the head. Like if you're following what's happening in zero knowledge the last 5 years, they can now do, I think on Oakland, there's going to be a couple of papers, they're doing billion gates. We're nowhere near that. But that's because they're not using the vanilla MPC in the head. They're doing a lot of pre-computations, which now that we have that first version of MPC in the head, you can start looking at these more advanced. So it's unfortunately always going to be lagging. But in principle, you can model all the new models that have MPC schemes that have, zero knowledge proofs that have pre-computation built on MPC in the head, and maybe go up to like millions of gates. I think that's doable to get to maybe 10 million, but the billion gates, that's gonna require optimization. We're going to require a lot of optimizing, like parallelism, which is not supported in EasyCrypt yet. But that's all solvable, I think, based on this. Anyway, yeah.
So you're saying I guess if the circuit is bigger, it takes longer, but like if you, why is that the prover verifier time grows proportionate to the circuit size? Like, is this necessary?
No. This is the very first. Doesn't involve any pre-computation. Like the MPC.
What about the prover time, not the time of actually running the thing? This is about the prover time.
Yeah, this is the prover time.
So this is the zero knowledge. Is this are you formally verifying it, or it's like you're just implementing the zero knowledge? Right?
No, we formally verify.
This is the prover for the zero knowledge, not the prover, not the formal verification.
Yeah. No. This is the executable code. This is like the extracted prover and verifier. This is how much time it would have taken to run. No. The verification is. This is the performance of the actual extracted code for the zero knowledge proof for circuits that had 100, 1,000, 10,000 gates.
Okay.
And these are random functions. There are other, this was part of Civ, so there was very specific like matrix functions that they want, matrix multiplication, the other circuits that I have. No, I don't have it here. I mean, this version had the number of lines of code. So like all the abstract definitions, like 12,000 lines of code. The actual implementation here of BGW was 9,000. This one, 8,000 parable. It doesn't take that long to verify these, if that's what you're asking. All right, so I mean, whenever I talk about this, probably not this community, but be surprised of how much pushback you're getting. I mean, we often get a lot of pushback from cryptographers, especially. It's like, what if your security definition or abstract specification are wrong? So I always include this slide. I guess I'm like, how is that different from on paper? I personally think it's not. Actually, as a matter of fact, it's faster. Now we have all the same definitions, can easily import them, work on them. Yeah, I mean, I guess the only viable thing and related to your question is like, what if what happens with EasyCrypt? I mean, EasyCrypt is still not as widely used. That is a problem, but I guess if you, like I got to learn, I'm not even there at like PVS or looking at Isabel or COG or Easy. They're not that far from each other. And once you get used to one of them, you can actually transfer the knowledge. But I think we do need more tools. I'm actually after this, I'll go and look at some of the other tools. I personally haven't looked at them. But I think ideally in 10 years, we'd be using something like EasyCrypt when we design protocols, not after we have the protocol and verified it. Anyway, so I mean, the point of this talk is to show that, and this line of work is that I think at this point, computer-aided verification synthesis of very complex protocols. I mean, what's the next level of complexity? I would say FHE and maybe something like obfuscation. And this is it. These are the most complex objects in cryptography. And if we can do MPC and zero knowledge, I think at this point, hopefully, people should be convinced that this should, in the long term, make its way to actual production. I mean, I would love to see a day where somebody's actually running a Byzantine agreement or broadcast protocol or MPC protocol that is formally verified. Performance overheads, we can keep optimizing there, but I think it's the UC and other primitives will be the most interesting. And then this is orthogonal though. If you go to the low end at simpler cryptographic protocols and start looking at hardware software code design, I have a lot of work over the last years at Usenix Security and other conference on looking at hardware software code design for embedded system for remote attestation. That's a simple challenge response protocol. There you can start talking about formally verifying the hardware and software, then you get much stronger security guarantees. Ideally, we'll get there at some point in the future, but for now, just sticking to embedded systems is enough. That's it. Questions?
I guess I just have one quick question.
Sure.
Do you remember exactly what is the security? I mean, this is related to one of the questions you had. Like, what is the theorem that you prove for the MPC? Like, I guess there are many different versions of definitions.
Right. So for MPC, I can extract that. For MPC is basically, okay, so I mean, at the abstract level, for instance, at the abstract level, what you're proving is that if an adversary, for secret sharing, for instance, like if an adversary doesn't exceed the threshold of corruption and over whatever it was, I think it was n over 3, then you have, you define secrecy for secret sharing that you cannot distinguish the shares of random secret from, sorry, you cannot distinguish the shares from it's a game. Yeah.
What about the MPC? Like, is it a simulation-based solution or is it like?
Oh, yeah, it's a simulation-based solution.
I see. So the secret sharing, is it information theoretic or is it computation?
The normal secret sharing is information theoretic. The VSS was computation. Then it used Peters.
I see. Okay. Our next speaker is Anna. She is a professor from RPI. And she has done a lot of nice work at the intersection of crypto and PL, formal verification as well.
Thank you. Just trying to figure out. So, Andrew, can you help with this?
Just pop your computer down here.
Oh, that's the battery will stay alive.
Here, plug you in.
Thank you.
Hang on a second.
Okay.
Now you can share your screen.
Continue. Audio. Sorry.
Leave audio.
Sorry, I don't think that. Oh, no. I had it on, but when I relaunched the meeting, it just turned off. So, sorry. Okay. So, hello, everyone, and I want to thank Elaine and Andrew again for inviting me to give a talk here. So, our work is on what we call compilation and backend independent optimizations for MPC. And our team consists of Benjamin Levy and Ben Sherman. And Benjamin is actually an undergrad at RPI, and Ben is also an RPI grad, but he stayed for a year to complete his master's. And they're the primary authors of this work. So this is also joint work with Ishak and Vasilis on the crypto side from Purdue. And I'm Anna, and I'm the very fearful leader of this group. So I have to say I'm anxious standing here and giving this talk because so it straddles different areas, MPC and high performance computing. And these are areas with very deep and broad body of work. And I'm not an expert in any of these areas. So my primary expertise is program analysis, pointer analysis, and CFL reachability based program analysis, according to the Toronto paper matching system, at least. And what I like to work on is program analysis in different applications of program analysis in different domains. And I worked a few years ago with Ishak and Vasilis on protocol mixing for MPC, and I guess that's why I'm here. But since then, I haven't had much chance to work in this area until recently, until Benjamin and Ben joined us, and they do this great work. So, and I just want to say that this is all kind of ongoing work, work in progress, ideas that we've had, some things that we've done. And I'm very eager to hear everyone's feedback. Thank you. So programming technology for MPC has seen significant advances in recent years. And so my view of all this work in the area has been that, well, since the early compilers, more recent work has focused on what I call the back end of the classical compiler and the front end of the classical compiler. And so work that comes from the crypto community would focus on the design and implementation of efficient cryptographic primitives. For example, the ABI and motion work, and work from the PL community would focus more on the programming language and design of type systems and verification and so on. So we've thought that there is a lot less work on kind of the middle end of the compiler. This is the central thesis of what we're trying to do. And so that's why we are trying to work on an intermediate language, which we call MPC source, and what we call backend independent optimization. So in a close analogy to the machine learning independent, the machine independent optimizations in the classical compiler. And so this is kind of the picture of what we're trying to do. There's the different front ends that we can compile to our intermediate representation MPC source. Then we'll implement different optimizations and produce optimized MPC source, and then we can compile this optimized MPC source to one of the cryptographic frameworks. And just to make sure what we have done, so what we have done is a lot less general than some of the works that we had presented here today. So we've started with a very simple source language close to the minimal imperative syntax known as IMP, and we call it MPC source. And we've compiled it to our MPC source intermediate language. And then we have implemented one specific optimization, SIMD vectorization, produced vectorized MPC source, and then we translated this vectorized MPC source into the motion framework. And so the motion framework, I think, is kind of the descendant of the ABY framework, and it supports n-party computation, full threshold security, if I'm getting these terms right. And yeah. So, but the central thesis and what I have been thinking about, and I've heard these ideas now from several of the speakers. So, yeah, I'm glad, is that there's many different optimizations that are available at the level of MPC source. So MPC source has this nice structure that's very suitable for program analysis and optimizations, and we can apply classical compiler optimizations, but also optimizations that specifically target MPC. And so one is SIMD vectorization. So it's known that if we execute n operations at once in a vectorized manner in MPC framework, so that's a lot more efficient than executing these n operations one by one. And this is one optimization. So another optimization is protocol mixing. So we heard a bit about protocol mixing and protocol selection. Also scheduling, I think scheduling at the level of a loop, also scheduling the different iterations of the same loop. I think there's interesting problems there. Also detecting associative loops, and also divide and conquer parallelization, and so on. And so the way I think about all of these optimizations, so this is the one that we have actually done and we've shown performance improvement. And then there is the ones that I call kind of known unknowns. So I know that there will be performance improvement, but we haven't implemented this and we haven't integrated this into our compiler framework. And there is unknown unknowns, so optimizations that are there and are yet to be discovered as we extend our compiler with more functionality. And I think what's interesting, and it's an interesting research question, is that these optimizations closely interact with each other, and the order in which we apply the optimizations matter, and it's an interesting research question. So just as in the classical compiler, so the order in which we apply optimizations matters and leads to performance improvement. So yeah, and I'll start with a running example. So this is the kind of canonical example in MPC compiler papers, biometric matching, and just brief introduction. So here we take one vector of J features as input and a database of I vectors. And the purpose of this program is to compute the minimal Euclidean distance between the vector C and the database of vectors S. And there is many different ways that we can write this program. Now we deliberately, for the purposes of our work, we deliberately wrote kind of the most straightforward implementation. Here we're just iterating over the vectors in the database S, and then we iterate over the features in the vector and compute the sum, and then we update the sum if we need to. We also keep track of the index of the closest match. And so yeah, one point that I wanted to make is that well, it's well known in the MPC compiler literature that biometric matching benefits from protocol mixing. And but this depends on what's the program that the mixer starts with. And so, for example, if the mixer starts with an iterative version of the program like this one, then it may not benefit from protocol mixing. So this is because the cost of executing unamortized arithmetic operations is actually very high, and it may turn out that, well, the cost of executing the arithmetic operations one by one in unamortized way using the arithmetic GMW sharing scheme and protocol plus the cost of conversion is actually larger than the cost of executing these arithmetic operations using YAO sharing. And yeah, and so in this case, it may turn out that indeed the cost of executing the arithmetic operations is larger, and sharing and protocol mixing will not be beneficial. And the picture changes dramatically if the mixer analyzes a vectorized program. And in a vectorized program, so we have the subtraction and the multiplication and the sum vectorized. And so that means that we can plug in now the amortized costs for these operations, and the amortized costs are substantially lower. And when we plug in the numbers in this inequality, then indeed we find out that doing protocol mixing helps a lot. And I just wanted to put this as a side note that I plugged in the numbers that we benchmarked in our work a couple of years ago, but these numbers that we benchmarked now didn't make much sense in some ways to us. And as far as I know, so this is kind of an interesting problem, benchmarking and computing correct costs, correct estimates for these operations. So if anyone knows about work that's done this, and there are some accurate costs that we can plug in this kind of optimizations, I'll be glad to hear about. So, okay, so moving on to describe, yes.
So are you like, does your language support dynamic memory accesses, like indexing into an array where the index is a secret variable? Do you compile that just to circuits, or are you using that?
No, at this point it doesn't support, yeah, it doesn't support this. So I was going to mention this, that yeah, this is a restriction at this point, but yeah, we probably will extend, or at least we'll look at extending. Yeah, thank you. And yeah, so I'll talk about the MPC source intermediate language that we work with, then our vectorization algorithm, the experimental result related work, and we'll conclude with a brief discussion of future work. So yeah, so our MPC source intermediate language defined by construction. So we start from the source language, and as I mentioned, so the source language is just this minimal imperative syntax, close to the minimal imperative syntax. We have assignment statements, we have if then else, And we have for loops that are restricted. So the induction variable ranges from 0 to some compile time constant. And so we impose some semantic restrictions on this language. And so this is Elaine's question that, yeah, we don't support at this point array accesses that are non-plain text expressions. And also some of the restrictions are just inherent to MPC, I think. For example, the loop bounds are compile time constants. Then we also don't support dynamic accesses, so they have to be plain text. And some of the restrictions are just implementation restrictions that we plan to relax in future versions of our compiler. Yes.
So like, what kind of types do you support on the variables? Like, I guess like some earlier works have shown if you like enrich the types with like the bit length and stuff, bit width and stuff, it can help a lot in the compiler optimization. So, I mean, this language doesn't show any type for the variable. But is it like a bit or is it like a 32-bit integer?
Integer
or is it
and
like a 5-bit integer. Do you support these like a variable bit with variables?
So yeah, thank you. We support just integers and booleans, and we worked in our empirical results with 32-bit integers. But
so you cannot, if I only need 5 bits, we cannot tell the compiler I only need 5 bits.
yeah, no, we cannot. Yeah.
And those actually will help a lot in practice. That's what previous work has shown.
Thank you. So yeah, we and yeah. So and yeah, how do we construct the MPC source representation? So we start from our source syntax, and we move on to the tree address CFG, control flow graph representation, and then we run Cytrons algorithm and create the SSA form of the source. And so from the SSA form, then it's easy to move the conditional phi nodes in the SSA form turn into mux nodes, and the loop phi nodes are turned into what we call pseudo phi nodes. And then we linearize and produce the MPC source. And so basically what's I think an interesting point here is that so we start from the AST based representation, and we move into CFG, and then we move back to something that's more like an AST representation. But we are going through the CFG representation because this is the input to Cytrons algorithm. So in order to run the Cytrons algorithm and compute SSA form efficiently, so we have to go through this representation. And yeah, so this is the example. Yes.
So these pseudo phi nodes, those are there because you're going to unroll the loops. Is that what's going on? What makes them pseudo?
So they're there because the MPC eventually unrolls the loops. Yes. Yeah. So yeah, here's the example again. And so the notable points, the MPC source is this linear block structured SSA form, which is very easy to analyze. And we have just the if then else conditionals turn into straight line code. And here is what we call the pseudo phi nodes, because the loop eventually in the MPC gets unrolled. And it has very simple semantics. These are the accumulators that accumulate values in the loops. And so the phi nodes, yeah, it's defined in terms of the induction variable of the corresponding loop. So if J is the induction variable is 0, then this evaluates to the first argument. Otherwise, it evaluates to the second argument, which is the result of the previous iteration. So yeah, and we keep these nodes in our intermediate representation. And yeah, and we also have source semantics, which I said it has this AST structure. So we do have to go from an AST to CFG and then back to an AST. And we've defined this linearization semantics also, which just unrolls unrolls the loops in the SSA form. And the reason why this was useful for us is that we can reason about diffuse relations, and we can reason about the program, the transport program preserving the diffuse relations and preserving the semantics of the original program. So the next step here is our vectorization algorithm, which is very simple due to the linear block structured SSA form representation that we start with. And it has three phases. The first one is scalar expansion. The second one is loop vectorization, which I think is very similar to the classical work by Allen and Kennedy on loop parallelization on Fortran. And the third phase is cleaning up redundant dimensions. So now scalar expansion, what the scalar expansion phase does, it expands each variable to the corresponding loop nest to improve the opportunities for vectorization. So for example, here, this variable, which is nested in the two loops, is turns into a two-dimensional array. Then we track diffuse relations. And if we have a def from an outer loop or lower dimension to a use in an inner loop or a higher dimension, then we expand the dimensionality with the helper function. So here, for example, the sum, which is a one-dimensional array, turns into a two-dimensional array. And similarly, if we have a diffuse from an inner loop to an outer loop, then we'll drop the dimensionality, which in this case just gives us the result of the last iteration of this loop. And the next phase is, as I said, so standard vectorization analysis. We'll consider the cycles in the loop starting from the innermost loop, and the fine nodes here are particularly useful because they can serve as anchors for our analysis, for our cycles. Then we'll compute the cycles, and those statements that are in the cycles, they will remain in the loop, while the rest of the statements will be extracted out of the loop. Then the outer loop, there is now two cycles of fine nodes, so the min sum and the min index fine nodes, and this now isolates the code for the for loop, and the rest of the statements are extracted outside of the for loop, and they're vectorized. And so now we can have the for j loop partially vectorized. So it's vectorized along the I dimension, but it's sequential along the j dimension. So we have basically what we do is we compute all the sums in parallel for the I vectors in the database, but the partial sums are computed sequentially. And we also have the cleanup phase. The cleanup phase just cleans up some of the redundant dimensions. So it does basic copy propagation and some content propagation, and removes redundant dimensions. So here's the final code. So one interesting extension that we did to the basic vectorization analysis was the extension with array writes. So with array writes, classical SSA handling of arrays may give rise to spurious edges. And so we used Z3 to reason about accesses, read and write accesses, and remove certain redundant back edges, remove also certain redundant fine nodes. And this reduces essentially the problem to the previous case and nicely integrated with our basic vectorization algorithm, and gave us a lot of opportunities for vectorization in our benchmarks. So yes.
So does that amount to doing kind of an alias analysis on the elements of the array?
Yeah, yeah. It boiled down to something like that. Yes.
It seems like if you introduce some like parallel for like some kind of parallel programming syntax in the source language, a lot of this can be made very easy, right?
Yep. Actually, our intermediate language MPC source introduces some form of parallel syntax, and so you can actually incorporate this in the source language. Yeah. So, and so yeah. Now moving on to the compiler backend. And what we did, so we used the motion framework as our backend. And it supports simplified operations, supports different protocols for mixing. And what we did was we took our MPC source and we translated it to Motion C++. Then we used the motion framework to generate the circuits. So we did several sets of experiments. We started with the iterative MPC and the iterative MPC representation, the original program, and we constructed the Motion C++ and then generated the iterative circuit. We also took the vectorized MPC source and again generated Motion C++ using the same primitives that they had, and we constructed the vectorized circuit, and we instantiated these two circuits with two protocols, Boolean GMW and BMR. Yeah, so a bit more on the compiler backend. How much time do I have? So
it's supposed to be a couple more minutes, but I think you started a few minutes late. So you
Okay.
Thanks.
Yeah, so our compiler backend, so we have a very simple qualifier system that we use. We will annotate the shared variables that are represented using sharing schemes and protocol, and are computed upon using secure protocols. For example, here the C and S variables are shared. Everything else is by default plain text, and we use a very simple taint analysis because we just have this positive negative qualifier system, and we partition the program into shared variables and shared instructions, and plain text variables and plain text instructions. And from that point, we just translate the MPC source into Motion C++, and translation is very straightforward. So next I'll talk about our experimental results. The benchmarks that we collected, we ran this on standard benchmarks from the MPC compiler literature, so DY and HiCC. These are some of the benchmarks that we extracted. But we also went outside of the standard MPC benchmarks, and we collected benchmarks from the Parsint paper on synthesis of divide and conquer functionality, because, well, I think the next step is to implement some of these other optimizations, such as divide and conquer functionality. And so these are the benchmarks that we collected there. So probably about 16 or so, and we have more actually. We ran experiments. We ran experiments on small inputs, but we also ran experiments in the real world 2PC WAN setting and 2PC WAN setting. Our results were very good across the board. That there was significant improvement from vectorization across all of the metrics that we would be interested in. So circuit generation, for example, was about 20x time faster on the vectorized program compared to just the iterative one for both GMW and BMR, and also communication, significantly less bytes of communication were sent if we were running a vectorized program as expected. Also number of gates, substantial improvement in the number of gates, WAN setup time, again, 4x improvement on average for GMW, and about 20x improvement for BMR. WAN online time, and here we had basically the one data point where the vectorized version was worse than the iterative version. On one of these, what we call regular expression benchmarks from the Parsint paper, and we're still looking into to see why, what was causing the difference. We have some conjectures, yeah, we also took some other experiments, one setting. And I wanted to just talk about a caveat of what we have done. And basically, what we wanted to do is we wanted to compare our results, our numbers with some other programs that use MPC technology. And the only one that we found at this point was the Motion Native inner product program that came with the Motion compiler, and we compared the Motion Native program with the program that our compiler generated. And they had a simplified version written manually in Motion. And so we had our compiler generated simplified version, of course. And so when we ran this program, we ran the Motion Native and we ran our circuit. So our circuit was slower. And this is, of course, a negative result, but we saw a silver lining in it. So I'll just talk about it a bit. So you can see it can be split into two parts. So naturally, inner product. The first part is the simplified computation of the multiplication of the two arrays. And the second part is the accumulation loop. And this is the Motion Native code, and this is our generated code. And the first part, the simplified multiplication, well, the two versions generated essentially the same circuits. The second part, this is where our analysis, so our circuits were a lot slower than the simplified, than the Motion Native circuits. And you can see, so this is the pseudo-fine node translation, direct translation into Motion. And when we kind of took a closer look at this, so we found that the Motion compiler that generated the circuit special cased the plus equals operator and generated the circuit, which was a tree-like circuit, we believe. And this circuit, of course, is log n depth, and it's a lot faster. But when it faced the same, semantically the same accumulation loop, but syntactically a bit more complex, it could not generate the efficient circuit. It generated just a straight line circuit, which turned out to be a lot more expensive in GMW because addition in GMW is a non-local operation. And so the silver lining that we saw is that there is really a lot of opportunities for deeper semantic analysis that can be done here. So we should be able to detect this associative operation in this other syntactically more complex code, and apply the optimization and generate the more efficient circuit. And so there is a lot of related work in this area. So high performance computing, of course, vectorization is a classical problem. And so our main thesis here is that we can do vectorization natively at the level of MPC source. Because this is linear representation, we can interleave conditionals and we can interleave for loops, and we can have more opportunities for vectorization and apply vectorization a lot more aggressively because the representation is so simple. And also vectorization interacts very closely with other optimizations. So that's why we believe that it's important to do this at a single intermediate representation. And so this is my conclusion slide. We had MPC source, linear block structured SSA for Maiar, suitable for optimizations, and we've implemented one specific optimization, and we've implemented and evaluated it. So this is all available on GitHub, and my students have these very nice structures. Every phase of the compiler is illustrated with the intermediate result, and all the way to the Motion code that we generate. And so I think there is lots of opportunities for future work. And these are just some of the optimizations that we want to integrate in our compiler. I'm most excited about doing interprocedural optimization. So this is an area that I understand actually and maybe some program synthesis. So thank you very much.
I guess I just have a comment, maybe it's more of a comment than a
Mhm.
question. So like, I'm actually a big fan of having features in the high level language. Like, because I feel like high level language today are designed for like machines, like, you know, everything's 32 bits, integer are 64 bits, but like, you know, for something like NPC or zero knowledge, like it really matters whether it's 5 bits or 32 bits. Like if it's only 5 bits, you don't want to actually use 32 bits. I mean, there are many other examples, like for instance, I think for this that scalar vectorization, like if you can have parallelism in the high level language, that would facilitate a lot of these inferences. And I guess there are many other examples, like we had some earlier works, both for MPC and for zero knowledge. I guess for MPC it was called ObliVM, and we had like lots of abstractions that facilitate oblivious memory accuracy. Like, you know, if you have like language features like MapReduce and other simple features, like you could make the program oblivious in a way that's like asymptotically faster than using ORAN. So I personally feel like, you know, it is actually, well, I guess MPC is not fast enough yet. So given that we are in this stage, like it is actually matters to have these like features in the high level language. Maybe this is also relevant to like some of the earlier talks, like Thirsty. So and maybe Thirsty can also support like high level languages with these kind of features. I don't know, but I think this is like perhaps like a higher level discussion that maybe this community can think about. And this is also perhaps like where the crypto actually intersects with PL, because you know you have to understand the crypto to see what kind of features are useful in the high level language. So
Can you show your GitHub slide again? Just your GitHub URL?
Oh, yeah.
Okay, thank you.
I'm not sure because this is my GitHub and I might have to make it public. So if it's not public, just let me know. Yeah. So yeah, I can show the GitHub page.
yeah.
Thank you.
So let's take a short break. I guess we were supposed to have a 15-minute break, but we are running a little late. So why don't we take a 10-minute break and start at 2:50? Okay, sounds good. And we'll have shortcuts in the next session.
Yeah, I think it's not public.
Oh, it's not okay. Yeah, I can show you. Yeah. So.
On the schedule, and we can do it in a blockchain fashion. The previous block will mine the next block. The previous speaker will introduce the next speaker. So the first speaker is Josh Gancher. Hello, Josh.
Yeah, there he is.
Yeah, he's there. Okay, yeah, so Josh will kick things off here.
I'm screen sharing.
It is not showing your screen sharing, actually. You may be having the same trouble that I did before.
I mind the first block.
Okay.
I go to share screen and then
Yeah, are you mirroring your screen? I found that if it's not mirrored, that seems to.
How do I not mirror my screen?
Yeah, that's a good question. I was struggling with that earlier because they changed the UI.
Do I want to just do my desktop? But not,
You could do your desktop.
I mean, if I could just do that. Oh,
No, something chat. It detected you changed something, but it didn't actually.
oh, okay. Well,
All right.
I was gonna prefer to look at my.
And I should warn you that I'm going to have to be pretty ruthless about cutting people off if we run out of time.
So I guess I'll just like, does that work? Yeah.
That's my desktop.
Yeah.
Okay, why is this? Sorry, this is not.
Yeah, I think it's on your end, right?
There we go.
No, if I move my, okay, I'll just go from. Oh, okay. Am I good? You're good. Cool. Hi, I'm Josh. I'm a postdoc under Brandon Parno at CMU.
and I'll be talking about the beginnings of our work on end-to-end verification for security protocols. So by security protocols, I mean not like MPC or ZKP, but I mean things that basically protect communication across the internet. So like things like TLS or related protocols like QUIC, or like the noise framework, which we heard a little bit from Nick's talk. So these protocols are super ubiquitous, with like most of the internet being protected by TLS, but they're also extremely complicated, making use of like fancy mechanisms like authenticated encryption, digital signatures, PRS, and so on. And that's not to mention like application-specific requirements like cryptographic agility for TLS or concurrency issues. So we aim to advance the state of the art here with OWL, which is an end-to-end, which will be an end-to-end compositional framework for building protocols that are secure by construction. I just should emphasize here, this is all super preliminary work. So what we'll have here is we'll start with some simple functional core language. And it'll be designed to support verification at all stages of the pipeline. So we'll guarantee computational cryptographic security, just like the guarantees you get from EasyCrypt or Squirrel, using concrete crypto assumptions. You also get high performance implementation through some kind of verified compilation from the core language. And you also support other lighter verification tasks like symbolic testing, which is useful for debugging protocols. So I'll first talk about this computational cryptographic security. So the thing that we're really trying to advance here is compositionality of these proofs. So TLS is extremely complicated. You can't think about it all at once, but it's easier to think about it if you break it up into 3 separate subprotocols. So first you have the handshake, which establishes the shared secret. You have key derivation, which derives new keys from old ones using some kind of PRF. And then you have secure transport, which if you already have the key set up, this tells you how to securely send and receive information. And ideally, because we're doing verification, you like to verify that if all of the 3 subprotocols are secure independently and maintain some invariance, then TLS as a whole is secure. Unfortunately, using modern tools, it's not really feasible to do this mechanically. So some tools are like very automatic and somewhat easy to use, but they are like whole protocol proof methods. So like CryptoVerify and Squirrel assume you know the whole protocol at once, which precludes you from being able to compose subprotocols together. Other provers are expressive enough to do this kind of thing, but they're just not scalable at all because you have to handwrite your own crypto reductions, which would be not very doable for something like TLS. So instead, what we're going to do is we're going to use techniques from information flow adapted for computational cryptography. So the reason to use information flow, of course, is you're combining security concerns with compositionality. So classically in IFC, if E has label L, that means something like E depends on data that's labeled as L. Instead, for doing easy reasoning about crypto, what we'll say is that E is PPT simulatable from L. So given a probabilistic polynomial times simulator, you can use the cryptographic resources in the label L to simulate E. So here, this thing L is not only a label, but it also stands for things like secret nonces or like an encryption oracle or like a random oracle. So to give a bit more information about how this will work, here is our like very basic typing judgment. E here is a program, gamma is a normal like typing context, L is a label, and the sigma thing here is a name context. So similar to prior work, we have this concept of names, which are basically formal pieces of randomness you want to keep secret, like a key. Names are attached to name types. So 2 example name types are like Diffie-Hellman secrets or an symmetric encryption key. And here, this key is crucially attached to a label L. Labels are a bit different than normal in IFC because normally in IFC because they're attached to these names. So for instance, labels can be given by a single name, like a key K or Diffie-Hellman secret X, or the AND of 2 labels, or these 2 special labels, PK of N and Inc of N. So here, PK of N is like the Diffie-Hellman public key if N is a Diffie-Hellman secret. Similarly, Inc of N is basically an encryption under N if N is an encryption key. Labels here actually have a cryptographic semantics via oracles. So given a label, there's an oracle for that label. So the oracle for the label that's just N just outputs N. The oracle for PK of N outputs the Diffie-Hellman public key of N. The oracle for Inc of N is an actual encryption oracle for N.
And then the oracle for the and of two labels is just the combined oracles for the two labels. So the basic invariant of our type system is essentially that if X has label L, then X is basically the value of X is PPT constructible using the oracle corresponding to L given the simulator. And to make this precise, this basic invariant is stated against a distinguisher, and the distinguisher is quantified using this observer label L sub O, which says what other information in your type context the observer is allowed to observe. So for instance, the observer says given information at L sub O, it cannot tell the value of X from a simulated value using the oracle O of L. So switching gears a little bit, now I'll just talk a little bit about this high performance implementation. The basic pipeline will look like this. You start with your core language, that's your functional spec. We'll then apply some amount of annotations, hopefully verified in F star, to get some intermediate representation that I'll talk about in a second. Given that, we'll then perform a verified F star interpretation into the steal effect, where again, steal is like a embedding of concurrent separation logic inside of F star. We'll do so with a lot of help from PLCrypt, which is a previous effort in verifying cryptographic implementations, and everparse, which is a verified library of parsers and deparsers in F star. And then finally, we can leverage existing extraction toolchains for F star to turn the steal code into C, the verified C code. So just to wrap up, let me just show you some issues with this compilation. So consider this very basic program. You have three variables, sk, x, y, and z. So what you do is you concatenate x, y, and z together, sign it under sk, and that's your program. So a very naive compilation is you basically just allocate a new buffer for every intermediate value. So you have a buffer for x and for y and z. You have a buffer for x concatenated with y and z. And then you have another buffer for this signature of the concatenation. And while this is very easy to prove correct, it's not very feasible for being used in a high performance setting. So instead, what we're going to do is compile a code that looks kind of like this. So first we'll have length inferences. So every variable in the functional spec will have some amount of length information that are typed to it. So for instance, sk has length 32 because that's required by the signature algorithm. These lengths are also very useful for length dependent operations like concatenation. Speaking of concatenation, we'll perform some amount of specialization. So concat up here looks like just a pure function, but down here it's actually compiled into consecutive mem copies. And these consecutive mem copies are done in this scratch buffer buff to hold the intermediate results. Now that you're using the scratch buffer, you need to worry about destructive updates. So, when you're overriding the scratch buffer, you're actually overriding the information that was in the buffer before. So our compiler needs to manage a delicate balance between reusing the same memory for performance reasons and also remembering old subcomputations to be able to maximize sharing of resources. So just to wrap up, we're working on an end-to-end verification framework for security protocols. Hopefully we'll reveal new connections between information flow and cryptography, and we'll do so with high performance implementations that are extracted using F star. I welcome any feedback, and here's my email address if you want to ask questions. Thank you. Do you have time for questions?
Yeah, I think so.
Okay.
Yeah. So with labels, you can simulate, and simulation is relative to the observer.
Mm-hmm.
So how much power can you give the observer? Can it actually see? Can it try to see timing channels and try to differentiate between how long a instruction takes, or does it only see memory locations access, or how much power can you give to it?
That's a good question. So the core language is kind of a pure functional language. So we're kind of assuming away all of the security issues coming from memory accesses, timing information. It's kind of a just like in EasyCrypt. Like EasyCrypt has the same kind of model where you don't worry about these like low-level timing information. Where you worry about that is when you compile to this verified implementation, you want to do so in a security preserving way, right? So you want to be able to compile and show that no adversary in the, just like in UC, you want to say that no adversary in the compiled program has more power than the adversary in the idealized functional spec.
Is there time for one more? Oh, okay.
All right, go ahead. Was that Owen?
Yeah, this is really cool work. I was just wondering if you could say like just a little bit more about how the oracles you're building with the label syntax, like how is it that you're using them? What do they feed into?
Yeah, so let me just show you, it will be scary, so don't worry too much about it. But let me just show you an example, a typing judgment. So how this typing judgment works is for this ink honest typing judgment, it says the encryption of some message T under K has a label, and the label is S and K and L of the length of T. So what this is saying is that the value of this encryption can be simulated if the simulator has access to enough information to construct the length of the message, which is often like public information, along with an encryption oracle to the key K. And again, this is done relative to this observer label also. Does that answer your question?
Yeah, sort of. It gives me a sense. I may chew on that and ask a question later.
Yeah,
cool, thanks.
Feel free to reach out to me though.
Yeah, sure.
So thank you, and let's let Priyanka get a chance to talk.
Share your screen. Looking good. Did you set it on the right side there? Or full screen?
Can you hear me? Okay, so hi everybody, I'm Priyanka and I am a grad student at UC Santa Cruz. So I'll be talking about applying replication and consensus securely with Packard. So this is a joint work with Maximilian from Chalmers and my advisor, Owen Norton. So I will start with giving you some, and by the way, this work is going to appear in CSF this year. So I'm going to start with giving you some background, some motivation behind this work. So, so we know that in modern day computing, we depend on distributed systems for almost all our online activities. So these distributed systems consist of a bunch of hosts, and these hosts communicate with each other, and they depend on each other for data and computations all the time. So one thing that is kept in mind while building this distributed systems is that there shouldn't be any single point of failure. So for instance, in this picture, if host A becomes offline, then it might create a network partition. So the tool that is used to get rid of such problems is replication. So let's add another host, host B, in this example, which is an exact replica of host A, so that when A becomes offline, B can perform the exact same computations, and it will also make the system more available. But there can be another situation where both A and B are available, but B becomes malicious. So in that case, when you replicate a computation on A and B, B might end up sending different value than A to a recipient host, say P1 in this case. So if that happens, then P1 wouldn't be able to decide which value to go for. So the way this kind of situations is handled is via consensus. So so let's add another host, host C, which is replica of A and B. And now if we replicate the same computation on A, B, and C, and if 2 out of these 3 hosts return same value to recipient P1, then P1 would know that a majority of the hosts have had consensus on a value. So in this way, we also get more integrity because now multiple hosts have computed the same value. So, replication and consensus, these are the 2 mechanisms used in quorum-based systems. So in this example, A, B, and C will form a 2x3 majority quorum system. So, but writing quorum-based systems can be challenging because of different reasons. Like maybe some part of the code needs to be replicated into the quorum instead of the whole code, and the programmer needs to identify those part of the code correctly. Maybe different part of the code need to be replicated in different quorums, and for that, the programmer needs to keep all the complicated trust relationships in mind while writing the code. And then there can be other mistakes from the programmer as well, like writing the wrong variable at wrong place may actually change the whole outcome of the program. And on top of those, there can be data dependency related problems, like secret values may flow to public domain, corrupted values may flow to honest hosts, and highly available data may erroneously depend on low available data. So the way this data dependency related problems are handled is via information flow control policies. Although confidentiality and integrity policies are well researched, availability policies are not researched that much. So the only work that we are aware of that talk about availability guarantees using information flow control policies, availability guarantees, using information flow control policies is from Singh and Myers. So in this work, we present FLACR, which stands for Flow Limited Authorization for Quorum Replication, and we address all the issues that I just described. So it's a core calculus, and it comes with semantics to support quorum-based programs. So it comes with a type system, and it adds availability policies to FLAM algebra, which already had integrity and availability policies. Integrity and confidentiality policies. So let us look into some of the FLACR language constructs that will enable a programmer to write quorum-based programs. So the first one is compare. So a compare of a program P replicated on hosts A and B will return a value if both the hosts A and B return same value. Otherwise, it will return a fail value, and in FLACR, fail will represent a value that is unavailable. So in distributed systems, compare will compare encodes consensus, and so another language construct is select. So select of a program P replicated on hosts A and B will return a value that is returned by host A. And if host A is unavailable, then it will return the value that is returned by host B. And if both are unavailable, then it will just return a fail value. So in distributed systems, select encodes replication. So with using this select and compare language constructs, we can write quorum-based programs. So this is just an example to write a program that runs on a 2x3 majority quorum system. So let's talk a little bit about type system, some program types. So type of program indicates how secure the program is. So that means it indicates who can read the result, who can influence the result, and who can actually fail the computation. So a program that is running on a quorum system, a FLACR program that is running on a quorum system, will essentially have type L sys-tau, where L is the security label that protects the evaluated value of type tau. Now this security label L should realize the confidentiality, integrity, and availability that the quorum system has to offer. Now, for this presentation, I'll only talk about availability and integrity. So we already saw how compare and select works. So the end result of a compare statement is a value if both the hosts A and B are available. So that means the availability of the end result is unilaterally controlled by both A and B, and which actually decreases the availability of the end result. So we represent the availability label of the end result as A, Boolean, or B. And the availability of the end result of a select statement would depend on availability of both the hosts A and B. As long as one of them is available, then the end result will be available. So we represent that as A, Boolean, and B. Now for integrity, the labels are even trickier because, so we'll see why. So the end result of a compare statement is a value only when both A and B return matching values. Now, it should have the combined integrity of both A and B, but we cannot actually say that because A, Boolean, and B is a principle that actually arbitrarily act for both A and B. So instead, what we want is to represent the fact that A and B had consensus over a value. And for that, we introduced a new binary operation, which we call partial and. So A partial and B integrity label on a value would mean that this value is a result of a consensus round between A and B. Similarly, the end result of a select is coming from either B or A. It never comes from both the hosts. And so it has integrity of either A or B. But again, we cannot represent that as A, Boolean, or B because A or B has lesser integrity than both A and B. So again, we introduce another binary operation, which we call partial or. So A partial or B, this label, this integrity label on a value would mean that the value has integrity of at most A or B. So this slide, in this slide, I just want to highlight some of the theoretical results that we had. We came up with a new attacker model, which is a little bit different than traditional IC-based systems attacker model. We have a defined toleration set for quorum systems. We identified a relation between a principal and type of a program. We also define valid quorum types. So using these definitions, we define and prove our availability non-interference. We also prove confidentiality and integrity non-interference theorems. And for detailed proofs, I encourage you to look at our technical report. And also this slide I came up with this, I mean, just this morning, because when I was listening to Josh's talk, I thought maybe if we can extend their label model with the FLACR policies to, also include quorum replication protocols and all. So that'll be an interesting thing to look at. So with that, I want to thank you for listening.
Any questions? How does the select work? I didn't understand what determines the outcome. Is it just like whichever gets?
Actually, no. So I'll share my screen now. So it always takes the output from the first host, and if the first host is not available, it will take the output of the second one. Yeah. So it's deterministic in that way.
I think next up is that's yeah. Yeah, thank you again.
All right, hello everybody. So today I'll be talking about the monadic composition of argument systems. And this is joint and ongoing work with Professor Brian Parnell. Now, in traditional cryptography, we're sort of used to just considering sequential composition or parallel composition, right? But what we've been learning today is that there's actually much richer notions of composition that we can consider in the context of cryptography. So today I'll be talking about how specifically we can consider monadic composition in the context of argument systems and how this can potentially improve how we reason about them and how we essentially can prove the security about them, okay? But before I begin, it's sort of important that I fix exactly what I mean by an argument of knowledge, okay? So an argument of knowledge is just an interactive protocol between a prover and a verifier, okay? In which a prover proves that it knows some secret witness W, okay, that satisfies some prescribed computational statement U with respect to some relation R, okay? And this is an interactive protocol, and eventually at the end of interaction, the verifier will eventually decide whether it believes the prover or not, okay? And for an example, imagine that U is maybe a 3-side instance and W is the corresponding assignment. So one of the things we've been realizing is that modern arguments are actually built in a much more modular and composable way nowadays, okay? What I mean by that is the arguments start with very complex statements like 3-sat, but then the prover and the verifier interact with each other and reduce it to the task of checking a slightly simpler statement. And they reduce that to the task of checking a simpler statement. And they keep doing this over and over until they eventually reduce it to the task of checking the trivial relation, which encodes 0 or 1. So to formalize the security of each of these steps and also make the composition operator explicit between each of these steps, we introduce a formalization called reductions of knowledge, okay? And a reduction of knowledge is essentially like an argument of knowledge, except the prover and the verifier reduce the task of checking the initial relation R1 to a slightly simpler relation R2, okay? So what happens explicitly is the prover starts with a statement witness pair U1, W1, okay, in the first relation. And together they interact a little bit, and eventually the verifier, instead of outputting 0 or 1, just outputs a new statement that it would like to check, U2, okay? And likewise, the prover outputs the corresponding witness W2. So to give you an example, imagine that the prover and the verifier want to check an inner product argument over size n vectors, okay? They can interact a little bit and reduce this to the task of checking inner product vectors over size n over 2 vectors, okay? And you can imagine that if we sort of sequentially compose these reductions of knowledge a bunch of times, we end up getting a full-on argument system for inner products. And it turns out this is exactly how inner product argument systems are built today. Okay, so it's sort of important that we take a step back and take a look at exactly what I mean by composition. So one of the things we realized is that reductions of knowledge give us a nice abstraction to view, steps of an argument system as maps between relations, okay? And when we view them as these maps, we can sort of view how to compose them and produce new reductions of knowledge that are more interesting and larger, okay? And this is something we prove in our work, that sequential composition of 2 reductions of knowledge results in a new reduction of knowledge, right? And this composition theorem ends up being a workhorse for showing that, well, if you have a bunch of reductions of knowledge, you can sequentially compose them and put together an argument of knowledge that is secure by default. Now, the thing is that there are a new class of argument systems that are becoming increasingly dominant that use a technique called recursive proof bootstrapping, okay? And what I mean by this is that the prover writes a proof about the existence of another proof, which itself could be talking about the existence of yet another proof, right? So as expected, these sorts of systems get increasingly complicated, okay? And when we try to reason about these sorts of systems using our nice modular techniques, our notions of composability start breaking down, right? And what I mean is that our standard composition operation of sequential composability is not powerful enough or not expressive enough to reason about recursive proof systems, okay? But one of the things we realized is that, well, okay, what if we change the composition operation itself, all right? So one of the things we realized is that, okay, in a recursive proof system, we can view, well, what is really happening when the prover is writing a proof about a proof. What it's doing is it's mapping a proof about one statement to a proof about another statement, okay? So now the question becomes, well, how can we define composition operations and reason modularly over these sorts of maps, okay? And this is where the notion of monadic composition comes in. We can potentially redefine the composition operation itself to be able to reason about these protocols. Okay, so today we don't have a result yet, okay? I wanna make that clear. But today I wanna try to propose a definition that can potentially try to answer how we contain the complexity of recursive proof systems, okay? So the core idea is that we want to be able to translate a proof of one statement into the proof of another statement without having to actually open up that proof and look at the witness that is encoding, okay? So formally, what's going on here is that imagine a transformation, okay, where we go from an initial relation that is over statement witness pairs to statement proof of witness pairs, okay? And what I mean by this is that the new verifier no longer cares to check that the prover actually has a witness, okay? It only cares to check that the prover has a proof of the witness, okay? And now the burning question becomes, well, if we had this sort of transformation, can we compose two reductions that output proofs of witnesses rather than just witnesses themselves, okay? And if you think about it, this is actually encoding the core question that a lot of people ask when reasoning about recursive proof systems, okay? The question is, so for what class of relations and what particular transformation can we generically augment an old proof and turn it into a new proof for a new statement? Again, without having to open up the proof itself and extract out the witness, all right? So this may all seem a little bit abstract, so let me give a practical example of why recursive proof systems are important, okay? And why the specific notion of the proof monad might be able to help in designing these sorts of systems. So imagine we want to prove the correctness of a blockchain, okay? This, in the most direct way, what this would involve is essentially taking all of the past transactions of a blockchain, okay? And writing a proof that they're all self-consistent with each other, okay? And this clearly becomes very unscalable because every time the blockchain updates itself, right, you're gonna have to write a new proof by looking at the entire state of the blockchain again, which is already very, very, very expensive, right? So thankfully, we do have techniques to get around this, okay? So in 2008, Valiant introduced a technique called incrementally verifiable computation, which shows that for certain classes of computation, you can actually take an old proof, okay, of maybe, let's just say n-1 steps of a computation, and then cheaply update it to turn it into a new proof of n steps of a computation, right? And that's exactly what we can do, right, with Valiant composition in this particular case. We can take a proof of n-1 steps of the blockchain and convert it to a proof of n steps of the blockchain, right? Now, what the proof monad gives us is essentially a way to sort of induce such a proof system automatically given a proof system that does the previous thing, right? So given the proof system that does what's on the top over there, we can run it through the proof monad almost as a compiler and essentially produce the second proof system over here, right? So essentially, we've abstracted the complicated parts about recursive proof systems into the composition operation itself, allowing us to define new techniques over new relations without actually having to reason about the nitty-gritty about how proofs over these relations would have to compose together. So I hope the major takeaway of today's talk is that monads offer a powerful notion of composition that sort of reinterprets how we should construct and reason about modern proof systems, okay? And I really hope that we can convince a lot of PL researchers to be able to use core ideas from type theory to reason about argument systems. And vice versa, I hope that we can have people working in argument system theory to be able to use core ideas from PL to be able to prove properties about large classes of systems over abstract types. Thank you.
So do you see, I'm trying to think about like the practical benefits here. Would this like let you start up a new blockchain miner more efficiently or something? Because you only have to check a proof as opposed to
right. Well, so
history.
Of course, yeah. So we already do have techniques to be able to take an existing proof of blockchain and then update it for another step, right? This is like incrementally verifiable computation. The problem is that these sorts of techniques, like they're very specific to a specific problem statement they're working over, right? And the practical application of this is to say, okay, well, now we can, for any sort of statement we can come up with, if we can sort of define a reduction of knowledge over it, we can define this really nice composable reduction of knowledge where we can just update the proofs in a nice way.
You seem to rely on like the algebraic group model or a particular kind of like non-falsifiable knowledge type assumptions, like those are sometimes tricky with recursive composition.
Right, absolutely. Yeah, so yeah, it turns out we do have to probably rely on a non-falsifiable assumption. It looks like almost every recursive proof system today has to use something along these lines. Yeah, I would assume that there's going to have to be something there, usually with something that has to do with instantiating the random oracle.
Is one or the other like a better fit for your kind of abstract?
I see. I mean, I feel like the algebraic group model would be cleaner and nicer, but for now, a knowledge assumption might have to do. Yeah.
Thank you. Our next speaker, Alexander Leon.
Thank you. Okay, so hi, I'm Alex. I'm a PhD student at ETH Zurich. And originally I was going to talk about fully homomorphic encryption compilers, sort of the challenges and the techniques that we use to compile these. However, based on the fact that we've seen a tiny bit of FHE compilation in some of the previous talks, and especially a lot of the challenges that are quite similar to the challenges in MPC and zero knowledge proofs, I've decided to quickly change around what this is going to be about based on some of the discussions I've had in the breaks and over lunch. And so instead, I want to talk about why your crypto compiler probably needs multi-level intermediate representations. Sorry?
Maybe get feedback. Just leave audio on your.
It's muted.
No, you need to leave audio because feedback loops go both directions.
I'm muted and
muted is not enough.
And I'm muted and like both, right? Like so, I'm not producing or inputting any audio. Sorry. I mean, feel free to zoom.
Sorry, go ahead.
Yeah. Okay, sorry. But yeah, so I want to talk about why we need these multi-level IRs, or why your crypto compiler probably needs them, of course, using the example of fully homomorphic encryption compilers. And so fully homomorphic encryption quite naturally lends itself to the abstraction model of circuits. And so it's easy to view an FHE compiler as something that takes a computer program and then turns it into a circuit in some sense, and then starts optimizing that circuit to finally produce the arithmetic circuit that is then actually executed. And so in FHE, the native operations are usually multiplications and additions, and so that's the kind of circuit you get out. However, it turns out that in practice, there is this additional step before you go to a circuit, which is high-level optimizations on the program. And that is what the new focus of this talk is going to be. And so the reason for this is that there's a bunch of different ways and application domains for FHE. Right? So ranging from using it in MPC protocols like private set intersection to using it for dedicated sort of single task applications like biomedical research, or just using it in privacy preserving machine learning. And all of these express their algorithms and programs in different paradigms, usually quite high level domain specific paradigms. And when we translate all of that into circuits, we lose a whole lot of information. And this is true even if the high level representation is something like C++, which I guess most PL people would not consider very high level, but compared to a circuit, it's incredibly high level. And so to give you an idea of this, I just want to show one high level optimization example. And so note that this is not a circuit, this is an AST to represent sort of the notion of we actually having a program with state and control flow. And so in FHE, there is, as is in many other things, the opportunity to explore SIMD-like parallelism, single instruction, multiple data. And I want to use this as an example of something that just wouldn't be feasible to do on the sort of unrolled circuits. So if you have an operation that is applied to all elements of a vector, it's quite easy to see how there's what's called batching, which puts multiple data values into a single ciphertext, allows you to do this in a very efficient way with a single instruction on a batch ciphertext. The problem with this is that usually programs aren't quite this easy, And the problem in FHE is a bit harder than standard vectorization because you just don't have the data movement operations like permuting or scattering and gathering that you would be used to in, let's say, AVX 512 instructions. The only thing you can do is do cyclical rotations. And so as a result, the challenge of translating an input program, like let's say this simple kernel that iterates over an image and computes sort of a blurring or sharpening function, depending on how you set the kernel, this is actually a quite drastic transformation if you translate it to FHE well. So you can see here that this inner loop that gets collapsed into this single sort of multi-operand addition. And then the outer two loops, well, they actually completely disappear because what we've done here is instead of iterating a kernel of an image, we've taken the image, copied it a few times and pushed it through the kernel in some sense in one operation using SIMD operations. And so in my work, I've actually built a compiler that does exactly these kind of transformations. It's currently under submission, but an earlier version is also up on archive, and it's called HECO, and it does automatic code optimizations for FHE. But today, I just want to talk about the kind of infrastructure that enables these high-level transformations. And that is MLIR, which is multi-level intermediate representations. And it's an open source project that lives in the same umbrella as the LLVM or client compilers. And so traditionally, compilers would have been designed in ye olden times to go straight from the source program to the output assembly. But obviously, over time, we've seen things like LLVM that reduces the gap that you have to cross, and also at the same time allows you to retarget the same intermediate representation to a whole different amount of baguettes. But if we look at more modern compilers than LLVM even, we start to see that these introduce additional higher level intermediate representations to model their input languages. And we see this sort of as we get more and more modern, the number of these representations grows. And especially for domain-specific languages, we tend to see a very large number of intermediate representations so that the individual lowering steps from one to the other become relatively easy to express. And so basically, what MLIR is, do I have a slide on this? No. What MLIR is the idea to abstract this left-hand side the same way LLVM abstracted sort of assembly in a generic framework. And MLIR specifically specifies a standard representation for intermediate representations. I know it's slightly meta. And so concretely, this is what a line of a program in an MLIR representation might look like. It's always in SSA, which is single static assignment, so you just don't write to the same variable twice. And it's basically a bunch of operations coming from certain dialects, which are just groups of operations and types. It has operands, it has types, it has results, right? It's a fairly self-explanatory in some sense syntax, but obviously it's not designed for us humans. It's designed to be efficiently computed on and translated. And so to give you an idea of what it looks like to actually build a real world crypto compiler with MLIR, this is a diagram I pulled from our compiler paper. And as you can see here, all the sort of the gray stuff is custom things we added for our domain specific tool or in terms of the top half in order to support our front end. But all of the stuff in the circle is free. That comes with MLIR. And so these are things like operations on tensors, operations on arrays, those kind of things, and arithmetic operations, the notion of constants and so on. Affine does loops, built-in function calls and so on. And the great thing is you don't just get a definition of what these things are. You don't just get a bunch of operations and types. These actually come with their own optimizations. So you don't have to worry about implementing common sub-expression elimination or constant folding. These are notions that are built into the MLIR framework. And if you set up your own dialect, your operation and types with the proper traits and sort of interfaces, they will actually naturally integrate with the existing ones. And the pre-existing optimizations will also apply to your code. So that means that if somebody multiplies something by 1, it's quite easy to tell MLIR that you please should not issue this very expensive FHE operation, which can take dozens of milliseconds to execute, thousands and thousands of cycles. Please don't issue that if it's just going to be multiplied by 1. And these are kind of the things you get for free when you use MLIR. And so to give you a more concrete idea, because this is still a very abstract drawing, this is what the program, or a very similar program to the one where I showed you the animation, looks like in a high-level intermediate representation. And I want to draw your attention, I don't think my mouse pointer shows up that well, but I want to draw your attention to the fact that virtually all of this program is expressed using generic MLIR terms. So arith.constant, func, find.for, all of these operations, arith.mul_i, add_i, and so on, they come from the base MLIR representation, and they just represent the program aspects of this. It only takes very few custom domain-specific operations like fhe.add and fhe.multiply, I think somewhere, to add to this and to turn it into an FHE program. And then instead of trying to translate this monster directly into a circuit and unroll all of these loops and just have this massive explosion of a circuit that would be completely impossible to work on, working on this high-level representation where we know that this is a loop, where we know that this is a tensor extraction operation, it allows us to actually batch this program. It actually allows us to batch this program, and so at the end of our high-level optimization, this is what's left. And so just as we saw before, the transformations here can be quite dramatic. And as a result, by the time we're done with the high-level representation, the circuit that we can now generate is much, much simpler. And that means that instead of first generating this massive circuit and then trying to somehow find how to optimize that down, by using multiple levels of intermediate representations, we can make things that would be completely infeasible to identify on circuits much, much simpler to find, and also much simpler and more efficient to implement in a compiler in terms of compile time. And of course, I don't show it here, but now it's very simple to actually generate a circuit from this. Okay, so that's my time. That's my somewhat improvised new talk. If you have any questions, I'd love to connect here, and I'll also obviously be at SMP next week. Thank you very much.
So going back to Elaine's question to somebody else earlier, I was just thinking that the code you just showed is that like the result of the optimization. It's kind of the code you would write if you were trying to write efficient code in something like NumPy or APL to go farther back, right? In a language which directly supports array constructs, you just code it that way naturally. So I kind of wonder, like, maybe we should be just trying to put the features into all of our programming languages.
I mean, it's not a nice way to program, right? I think people that have worked with these tools know that there's sort of this learning period where you have to go from imperative programming to vectorizing everything in your head. And I mean, eventually you wake up and you think it's the most natural thing to express everything as vector operations. But I think kind of the whole point of our compiler, for example, is to avoid that process, because again, like even if you know how to work in these tools, the data movement restrictions in FHE make it really hard to actually do this vectorization yourself.
Do you remember like Lambda composed Lambda, this like Chris Piker library?
Yes, LLL, yes.
Does that relate to this at all? I've always found that kind of surprising, but it would do like type level stuff, but it would be trying to pick some like FHE specific kind of trade-offs.
Yeah, so I think there is actually, I mean, somebody also did a Haskell-based compiler that did for FHE and stuff like that. I think, I don't remember what Lambda composition Lambda actually does in terms of optimizations. The problem with all of these approaches that use sort of fairly heavyweight techniques is that they just don't scale. So I think earlier on one of the slides, there was an example of Porcupine, which is a really cool FHE compiler that does similar things to us, sort of take a program and find out how to batch it. But that uses synthesis, and so it's kind of hopeless after you get to like any even larger toy examples just don't work anymore.
And very small programs.
Yeah, so like even like, you know, like think like, I mean, an FHE vector tends to be like 16,000 to 64,000 elements. The synthesis approach breaks at like 8 elements. And so you can sort of see, I mean, it's still a good tool to play around with if you're an expert and sort of discover new ways of doing things, but it's not something you can give to a non-expert and just compile something. And I have the feeling that with a lot of the heavyweight sort of type system, functional system based things, you run into the similar issue that eventually, as soon as you have an interesting program like the one I showed, which is still not a very complex program, right? Like a kernel of an image is not complex by programming standards. But for a lot of these tools, that would be a death sentence, and they just wouldn't be able to compile that.
Okay, thank you. right, Wu?
Yeah, just go ahead and share your screen.
Yeah, hi everyone. This is the last talk. So I'm going to talk about our recent work, complete characterization of game theoretically fair multi-party coin toss. This is a joint work with Gilad Asherov from Bar-Ilan University and my advisor Elaine. As a heads up, this work itself has nothing to do with PL or implementation. It is just pure crypto, but we do think that it is an interesting direction to mechanize our result. So yeah, Elaine and Andrew, they are two organizers of the workshop today, and they need to decide what to eat for the break. Elaine prefers sushi, but Andrew prefers cake. So, but they cannot persuade each other. So they say, okay, let's toss a random coin. If the output is 0, Elaine wins and we'll have sushi. Otherwise, we'll just have cake.
Okay, so Andrew, why? You're having cake.
Yes.
I prefer sushi, actually.
I should have asked, sorry. So yeah, they were not in the same city before the workshop. So they say, okay, let's do it on a blockchain. They each choose a random bit and put the random bit in the locked box. Then they post this locked box on the blockchain. If you're not familiar with blockchain, you can just think of it as a public bulletin board. And after they post this locked box, everyone can see it. Then after they both post this lockbox, they will post the key to the lockbox on the blockchain. So everyone can open the box and check the random bit inside. Let's say Andrew's random bit is 0 and Elaine's random bit is 1. So their joint output would be the XOR of these two random bits, which is 1. So Andrew wins. We had cake today. However, Elaine really wants to eat sushi. And after she saw Andrew's random bit 0 on the blockchain, she was thinking, okay, if I open my box, I'm gonna lose this game. I can choose not to open it. What will happen? In that case, Andrew just automatically wins because Elaine refused to open and everyone can see that she didn't open. So that means this outcome would be automatically 1. And still, we'll have cake. So this is the famous Blum's coin toss protocol back to 1983. And this coin toss protocol guarantees that any strategic player like Elaine cannot benefit herself by deviating from the protocol. So generally for coin toss protocol where our goal is to get a random coin, the fairness notion considered in traditional crypto literature is called strong fairness or unbiasability, which requires that any strategic player cannot bias the output towards either direction. Unfortunately, this is shown to be impossible by Cleat's result back to 1986. Indeed, we just saw that Elaine can always bias the output towards 1 by refusing to open her box. Instead, the fairness achieved by Blum's coin toss protocol is more of a game theory favor. So any strategic player cannot benefit herself. Now that we already have a 2-party fair coin toss, which is Blum's coin toss protocol, a natural question to ask is, can we do multi-party coin toss that achieve game theoretic fairness? So for multi-party coin toss protocol, we have a bunch of players who together want to toss a binary random coin. And they each has a preference of the output. Let's say Elaine, the other Andrew, and Karim, they prefer sushi, and Andrew Myers, Fraser, Josh, Anna, and Nikhil, they prefer cake. Some of them might form a coalition, and they would coordinate with each other, and they would try to deviate from the protocol to bias the output towards their preference. So the coalition in this figure, they prefers cake because the preference of a coalition is just the preference of the majority players in this coalition. So now, for multi-party coin toss, the game theoretic fairness notion is slightly different. Now we care about the behavior of a collision. So this fairness for multi-party coin toss requires that a collision cannot bias the output towards its preference. So if we have a coin toss protocol that is game theoretic fair against T-sized collision, then the honest protocol forms a T-sized collision resistant Nash equilibrium, because the best strategy for the player for the collision is just to follow the protocol honestly. So why do we care about this game theoretic fairness? Because strong fairness is shown to be impossible against half-sized collision. However, in many decentralized applications like voting on the blockchain, many pseudonyms are controlled by a same entity. And it is very likely that these pseudonyms form a majority-sized collision. They can coordinate with each other and they'll want to bias the output towards their preference. So we do want some meaningful fairness against majority-sized collision. And game theoretic fairness is exactly such slightly weaker than strong fairness, but still meaningful and suitable fairness notion for such decentralized applications. But still, is game theoretic fairness possible against half-sized collision? And the answer is yes. To convince you, I'll just show you a very cute strawman solution with 4 players. Let's say Kareem and Elaine, they prefer sushi, and let's call them sushi people. Fraser and Andrew, they prefer cake, so they are cake people. So this simple strawman solution works as follows. Each group, the sushi group and the cake group, they arbitrarily choose a representative. Let's say it's Fraser and Elaine. So Fraser and Elaine, they will do with each other and run this Blum's coin toss protocol. So the output of the Blum coin toss would be the output of this 4-party coin toss protocol. So now let's see why it is fair, game theoretically fair against collision of size 2. So first, if this collision contains a single sushi people and a single sushi person and a single cake person, then basically this collision has no preference. They don't care about the output. Then if this collision contains 2 sushi people, then by Blum's coin toss protocol, we know that Elaine cannot bias the output towards sushi. So this collision together, they cannot bias the output of the whole 4-party coin toss protocol and they cannot gain benefit. And the same argument works if this collision contains the 2 cake people. And we're good. So this tiny example is an evidence that we are able to achieve game theoretic fairness against half-size collision or even more. So in this work, we give a complete characterization of game theoretically fairness. We first give a game theoretically fair coin toss protocol against T-size collision. And we show that the game theoretic fairness is impossible against any T+1 sized collision. So I'll show you what T looks like. So in this plot, the XY axis denotes the number of sushi people and cake people respectively, and the Z axis is the size of the collision. This red plane is the boundary between feasibility and infeasibility of game theoretic fairness. Any region below this red plane, we can achieve game theoretic fairness with our coin toss protocol. And any region above this red plane, we show that it is impossible to achieve game theoretic fairness. Just as a comparison, this blue plane is the boundary for strong fairness. And below half-size collision, we can achieve strong fairness, and above that, we cannot. So the region between the red plane and the blue plane is exactly like the most interesting range of parameter that we cannot achieve strong fairness, yet we can achieve game theoretic fairness against majority size collision. So here are some future interesting direction. I think one interesting direction is to explore the game theoretic fair coin toss protocol for general K-weight coin toss, because in this work we only do for a binary coin toss. And another interesting direction is to formally define or mechanism our fairness notion and the formal verification of implementation to our protocol. And yeah, here's a perfect solution that everyone wins. Yeah, thank you so much. I'm happy to take any question. Yes.
We're all just transfixed by that cake thing. I don't really know.
Yeah.
We have to order this for our next.
Is that a real thing or is it something we're just like So you talked about the possibility, right?
Yeah.
And so from a slightly more practical point of view, is there like a, you know, any results on the sort of efficiency that's achievable? Because I mean, like, you know, the protocol you showed, the Stroman's protocol was quite simple, right?
Yeah.
And quite efficient. But I imagine that even if something is possible, it could require incredibly complex protocol, right? So do you have any intuition on sort of what these protocols, like what any of the instantiations look like?
Honestly, I don't have the sense for it, how implementation of that, our final protocol would look like, because our final protocol is actually more complex than the simple Stroman solution.
Oh, so it is a constructed proof then?
We give a protocol, yeah.
Yeah, so it'd be really interesting to see a couple sort of data points on when you instantiate it, like how expensive is it actually various codings in this area.
Yeah, that's a good question. I guess right now we have focused on feasibility. We haven't actually really tried to optimize the protocol. And we use some kind of an MPC technique, and I think the MPC part can be optimized a lot.
Yeah.
Okay, great. Thank you.
Thank you.